अमृतं ब्रह्मणि पर्जन्यो मे मूर्ध्निश्रितः मूर्धा हृदये हृदयं मयि अहममृते अमृतं ब्रह्मणि ईशानो मे मन्यो श्रितः मन्युर्हृदये हृदयं मयि अहममृते अमृतं ब्रह्मणि आत्मा आत्मनिश्रितः आत्मा हृदये हृदयं मयि अहममृते अमृतं ब्रह्मणि पुनर्म आत्मा पुनरायुरागात् पुनः प्राणः पुनराकूतमागात् वैश्वानरो रश्मिभिर्वावृधानः अन्तस्तिष्ठत्वमृतस्य गोपाः ॐ शान्ति शान्ति शान्तिः.
Om Shri Sai Ram. Offering our humble salutations at Bhagwan's divine lotus feet. Esteemed Vice Chancellor Professor B. Raghavendra Prasad, esteemed Director of the campus, Dr. Raghunath Sharma, distinguished Department Head for Chemistry, Professor Rajni Bhandari, Honorable Professors, esteemed invited speakers, respected faculty members, esteemed colleagues, and dear students, loving Sai Ram to all of you. With the divine blessings of our beloved Bhagwan, we will now light the ceremonial lamp marking the commencement of the two-day International Symposium on Chemistry for a Sustainable Future, Bridging Science and Society. We invite our respected elders to kindly come forward and light the ceremonial lamp. Sai Ram. We thank our esteemed elders for lighting the ceremonial lamp. We now welcome our distinguished invited speakers by offering them a unique plant which stands for sustainability, aloe vera. Its cultivation is eco-friendly with minimal water requirement and maintenance. It is increasingly used in the production of biodegradable products and is widely known for its health and wellness benefits. We request our esteemed invited speakers to kindly accept our token of love. Sai Ram. Sai Ram. Sai Ram. Sustainability should not be reduced to a simple buzzword. It should become a way of life carried forward with a sense of trusteeship, responsibility, and genuine concern for the present and future generation. As we face the ever increasing challenges of climate change, resource depletion, and environmental degradation, it is evident that science, especially chemistry, holds the key to a sustainable future. The scientific advancements we make in our laboratories must ultimately benefit the communities we inhabit. This is what we mean by bridging science and society. From the development of renewable energy sources like solar cells and biofuels, to the design of biodegradable materials that minimize waste, chemistry provides us with the tools we need to build a greener, more sustainable future. As we come together, let us appreciate this existential fact that we live in an interdependent reality and our lives, whether we like it or not, is intertwined with the world around us. Our every choice, every action has a direct or indirect impact on the way this world is shaping into future. With the spirit of Vasudeva Kutumbakam, whole world as one family, shining in our heart, let us embark on this unique learning experience on the essence and importance of sustainability in designing every walk of our life. It is now my privilege to invite the respected Department Head for Chemistry, Professor Rajni Bhandari, to deliver the welcome address. Professor Rajni Bhandari. Sai Ram.
Sai Ram, offering our collective pranams at the divine lotus feet of Bhagwan Shri Sita. I deem it my honor to extend a warm welcome to our esteemed Vice Chancellor, Professor B. Raghavendra Prasad, a hearty welcome to the eminent speakers who have joined us from India and abroad, Director of the campus, Dr. Raghunath Sharma, senior professors, colleagues, research scholars, and my dear students. A loving Sai Ram to everyone who has joined us physically and virtually. On behalf of the organizing committee, I welcome you all to the two-day International Symposium on Chemistry for a Sustainable Future, Bridging Science and Society, organized by the Department of Chemistry, SSSIHL Institute of Higher Learning. It is an honor to welcome you all to this important gathering where we come together to reflect on a theme that is not just timely, but essential for the well-being of our planet and future generations. That is sustainability. Sustainability is the foundation upon which we must build a better world for ourselves, for our children, and the countless generations that will follow. Sustainability is fundamentally about balance, the delicate balance between meeting our needs today while ensuring that the resources and ecosystems we rely on remain intact for the future. It calls for a long-term perspective in all aspects of life, from the food we eat, the energy we consume, to the materials we use and the way we treat our environment. It is about ensuring that our actions today do not deplete or damage the Earth's resources, but nurture and replenish them. Bhagwan Baba says, and I quote, "Human life will find fulfillment only when ecological balance is maintained. Balance in human life and balance in nature both are equally important," unquote. Sustainability is not just an environmental necessity, it is a social and economic imperative as well. Sustainable practices fuel innovation, open up new economic opportunities, and promote social equity. By embracing sustainability, we not only protect the environment, but we also foster a future that is resilient, just, and prosperous for all. Let's remind that sustainability is a journey, not a destination. It requires collective action, collaboration, and a shared commitment to changing the way we live and work. Every small action counts, whether it is conserving water, reducing waste, supporting ethical business, or advocating for policies that promote sustainability. Together, we have the power to create meaningful change. In academia, whether it is teaching, lab experiments, research, or publications, it is crucial to align our work with sustainability goals. We must make a concerted effort to integrate sustainability into every aspect of our academic activities. I would like to express our gratitude to the distinguished speakers joining us today from esteemed institutions such as the Central University, Indian Institute of Technology, Indian Institute of Science, Education and Research, International Advanced Research Center for Powdered Metallurgy and New Materials, Bhabha Atomic Research Center, Google, and Orkilon Surface Solutions. These thought leaders will share their cutting-edge research and innovations on key sustainability topics, which include advancements in green chemistry and sustainable manufacturing processes, applications of nanomaterials in environment monitoring and remediation, materials approach to sustainable energy, particularly solar energy, the cutting-edge intersection of artificial intelligence with healthcare and life sciences, innovative industrial practices that showcase chemistry's potential to drive environmental stewardship and strengthen economic resilience. In addition to these insightful talks, we have a variety of exciting activities planned, including poster presentation, oral presentations, along with live demonstrations of groundbreaking experiments. I urge all of you to make the most of this opportunity by engaging with experts, asking thought-provoking questions, and explore new ideas that can drive meaningful change. Thank you once again for being here today. Let's embark on this crucial journey towards sustainability together. Thank you, Sairam.
Thank you, ma'am, for your insightful and inspiring words, setting the theme for this two-day international symposium on chemistry for a sustainable future bridging science and society. It is now our privilege to welcome our Honorable Vice Chancellor, Professor Raghavendra Prasad, to deliver the welcome inaugural address. I request Sri Mainak Mukherjee, Research Scholar from the Department of Chemistry, to introduce and invite our Honorable Vice Chancellor. Sairam.
Om Shri Sai Ram. I offer my reverential pranams at Bhagwan's lotus feet. Today, I have been given this pleasant duty to invite and welcome our Honorable Vice Chancellor Sir to deliver the inaugural address. Before inviting him onto stage, I would like to briefly introduce him. First of all, we are very happy to have you, sir. Sir assumed charge as the 12th Vice Chancellor of this institute on 1st June 2023. He's a distinguished alumnus of this institute. Sir, having completed his master's from the Prasanthi Nilayam campus, went to join the Department of Physics in the Indian Institute of Science, Bangalore, on the year 1986. There, Sir worked on a project in the area of defense, which was of national importance. Having completed that, Sir went on to join the Indian Institute of Astrophysics in the year 1998. During his tenure over there, Sir worked as chairman of several scientific committees, and he was also heading several important projects. Sir even set up several R&D facilities, among which Sir set up Professor M.G.K. Menon Laboratory of Space Sciences to design, build, test, and calibrate space-based astronomy platforms. Sir was also the lead member of the UVIT Astrosat mission of ISRO. One of Sir's landmark contributions to this country was being appointed as the principal investigator of the VELC Aditya L1 solar mission of ISRO. There, Sir and his team worked on the primary payload of this mission, the VELC, which is the Visible Emission Line Coronagraph. This mission gave India its first solar observatory, located at the Lagrange point L1 between the Sun and the Earth. We as an institute are proud that Sir was a part of this mission. Sir also worked in different administrative positions, both at assessment and selection committees, at IIA and also at other prestigious academic institutions. Sir also has been importantly also in our global alumni group, and he has also been leading from the front several initiatives of this group for the past 35 years and more. Sir has interests in the area of sustainable energy technologies and environment, and has participated in many such projects, which was hosted by the Sri Sathya Sai Central Trust. With these few words, I would like to invite Professor Vice Chancellor Sir. Thank you, sir.
Om Shri Sai Ram. Offering my pranams at the divine lotus feet of our most revered founder chancellor, Bhagwan Shri Sai Baba. It's my privilege and honor to be here today. Multiple capacities, of course. We start with our very distinguished and eminent speakers who have taken off their very busy time from the very busy schedule. And I know how this symposium was planned. So at a very short notice, extremely kind to accept our invitation. It's just not a simple symposium what we talk about. It's basically like, we have started, SSSIHL Trust has started 2 years of celebrations, what's called SSSI centenary celebrations. So it's like Swami himself, Bhagwan Baba himself was so very particular about nature, energy, and thrust areas were energy and health. So that way he himself was a champion of so-called sustainable developments or sustainable future and sustainable living itself. So he initiated several programs. So this symposium particularly plays a very significant role. We are celebrating his advent, divine advent. And I should really compliment Professor Rajni Bhandari and her young faculty members, including the newest addition to the department, for enabling this wonderful program. And I think all of us should give a big hand to them for this amazing achievement. And all our colleagues over here and participants and my dearest students, it's with immense joy and deep sense of honor that I stand before you to inaugurate this international symposium on chemistry for a sustainable future, that is bridging science and society. When I see the entire brochure of this symposium and when I go through the list of speakers, that kind of talks, it serves as a crucial platform for advancing the dialogue on how chemistry can address some of the most urgent global sustainability challenges of our time. Of course, Professor Rajni Bhandari was saying sustainability is nothing but a way of living, not the end by itself. That's most important over here. I'm happy to inform you that at SSSIHL, particular week, we are celebrating with multiple events. In fact, last Saturday, about 3-4 days ago, we had one major discussion with several industrialists, including from energy sector. One of the speakers was saying, one of the industrialists was saying, the most important problem now is not generating green energy, because even to generate green energy, you are polluting the atmosphere. Generate cleaner energies, you are polluting. The most important challenge is decarbonization. So that's the one which everybody should focus on. And it was a very very interesting observation personally for me. And this particular symposium, I sort of hope that somewhere or other that topic also will be addressed by one of the eminent scholars over here. Of course, to celebrate this week, we have started this with the symposium, and then we have an ultra marathon going on. Started from the Vrindavan Hospital, SSSIHL Hospital at Whitefield, and it's an ultra marathon part. With all our campuses are also participating, and it is expected to arrive at Prasanthi Nilayam tomorrow evening. So that's again to bring in the awareness on environment and its importance, an ultra marathon. And of course, there are multiple other events parallelly going on in the institute. And we have also a green cell is very consciously trying to bring down our own, the carbon footprint. Some sense, try to go everywhere we want to go as a green campus and green institute. And we have very committed and faculty and students who are working on that. So this week is a very significant week for all of us. And when I see the topics in this event, they highlight groundbreaking advancements in green chemistry and innovative approaches to sustainable manufacturing. That's very important. Okay. It also promises enriching discussions on theoretical frameworks and the application of nanomaterials. That's key over here for environmental monitoring and remediation, with a special emphasis on atmospheric chemistry and sustainable technologies. I'm sure many of you are aware that our chemistry faculty published a very scholarly article about a month ago. It came on Nature Chemistry, front cover of the journal itself, on atmospheric monitoring. And of course, we all know that chemistry is the underlying principle or underlying force of all 17 UN SDGs. No matter which SDG you take, which SDG, you find that chemistry is the integral part of the whole thing, no matter what we take. And also the 5 C's of sustainability. I'm sure all of us know the 5 C's of sustainability. All that: cleanliness, community, culture, care, and corporate governance. Chemistry is the one which is all over there. As I see, one of the most exciting aspects of the symposium is focus on the intersection of artificial intelligence, again one more buzzword, with healthcare and life sciences. So at SSSIHL also we are playing a major role. In fact, we are giving a lot of thrust on incorporating AI in every stream of our curriculum, in every discipline, just to ensure that our students are at the forefront of all this. So, and also just to say that when I see that I do not want this symposium sort of classroom-like or intellectual exercise. Somewhere or other, when I was talking to some of our faculty members, they're all very on some very concrete outcomes, where all the experts over here and with our faculty members, and maybe a symposium statement, if it can come out, in our own interest, for our own future of the university and Prasanthi, Nilayam and also SSSI institutions. Be very grateful to have that, sir, because all of you are such experts, eminent people, and I would certainly request all of you to come out with a symposium statement itself on going further green in these campuses. And we also look forward to a lot of collaborative discussions, not just stop with that, and also inspire a lot of young minds, young researchers over here. And we have very, very dedicated students here. You find the students are different, in terms of their approach, the kind of training they get. And if you can really make them much more inspired at the end of the day, I think that will be the greatest achievement of this symposium. I'm very sure that and confident that outcomes of this event enrich our collective understanding and galvanize impactful actions towards building a sustainable future. And just to come back to our own interest, I want to share a couple of thoughts. The SSSI Central Trust itself started initiatives for green more than a decade ago. Historically, if you see, our founder Chancellor himself taught us how the ancient rishis, our own ancient scriptures, they worship nature. Of course, the West ridiculed, saying that Indians, we worship everything, including a leaf and tree and anything and everything. But now the world is realizing why that worship was integrated or implemented in our own system itself. Now we are realizing actually how important it is. They say that we have 33,000 crores, gods and things like that. But if you see the inner significance of all of that, it says that you respect everything, worship everything, take care of nature. If you take care of nature, then only you can take care of yourself and the entire humanity. That is the significance and culture of our Indian ancient wisdom. So the SSSI Central Trust also embarked on some of these initiatives a couple of decades ago. I recall, I'm sure many of our senior colleagues also recall, this entire region of Puttaparthi itself was a very arid and dry region. Okay? And now if you see, if you take an aerial survey of this entire, the Puttaparthi township and Prasanthi and SSSIHL district itself, it's probably the greenest area in the entire Rayalaseema area. So that is the level of initiative they started several decades ago. And of course, now we have gone, even the energy generation also, we have sort of initiated several mega solar power projects and many other projects also, where we try to go as green as possible and ensure that we be an example of what we talk about. So that's the path we are all treading, and then I'm sure this symposium will come out with a very clear mandate for all of us further going green, and I request all the students and faculty to take this going green or going clean as a very serious initiative and ensure that this university sort of becomes a role model. And with that, I wish this symposium very successful, outcome and very intellectually stimulating duration period for everybody over here, and particularly our young scholars and students over here. Thank you very much. Saira.
Thank you, sir, for your insightful words. Importance of actualizing the principles of sustainability as urbanization, effective collaborations to bring out tangible outcomes, and making us aware of the various initiatives taken up in our immediate surroundings in the form of solar energy, tree plantation, cleanliness. Thank you, sir. It is now time to commence technical session. During today's morning session, I have three invited speakers addressing all of us. The first speaker is Professor Gautam Brahmachari from the Laboratory of Natural Products and Organic Department of Chemistry, Vishwa Bharati University, Shantiniketan, West Bengal. Professor Gautam addressing us on the topic Electrosynthesis, an emerging green and powerful strategy in organic synthesis. I request our student Prayash Rai welcome Professor Gautam Brahmachari to the dais. Thank you.
Om Shri Sai, invoking Bhagwan's divine presence, a loving salam to one and all present here. My great honor to introduce our first speaker, National Symposium, Chemistry for a Sustainable Future, bridging the gap between science and Professor Gautam Brahmachari. Professor Brahmachari is a distinguished professor of organic chemistry, Vishwa Bharati University, Shantiniketan, with an impressive academic background, including a Doctor of Philosophy, Doctor of Science, as well as being a Fellow of the Royal Society. Professor Brahmachari has established himself as a leader in the field of synthetic organic natural products. Research focuses on the development of innovative synthetic chemistry and chemistry of natural, pioneering work on effective and practical, particularly in carbon hetero bond formation, has had significant impacts in group's advancements, CH functionalization, cascade reactions, and cross-coupling approaches have made important contributions of medicine. In addition to his work in synthetic chemistry, Professor Brahmachari has been a driving force in natural products chemistry, especially in the exploration of chemical profiles of traditionally used in medicinal plants. This research has illuminated the chemistry and biology of these plants, offering potential for new therapeutic discoveries. With over 26 years of experience in both teaching and research, Professor Brahmachari has authored an astounding 275 scientific publications, including original research papers, review articles, books, 6,830 citations, each index of 43, and invited book chapters. His work has garnered numerous accolades, including the prestigious RSI, Chemical Research Society of India Bronze Medal in 2021, the Professor Vasudev Banerjee Memorial Award, the Indian National Science Academy INS Award in 2019, Professor Kalam Best Teaching Faculty Award 2017, Academic Brilliance Award 2015, Excellence in Research, and many more recognizing his outstanding contributions to science and Professor Brahmachari's remarkable achievements have earned him global recognition. He was featured in the world ranking of top 2% scientists in organic chemistry, categorized by Stanford University 2020, 2021, and 2020. Also ranked among the top 0.05% of all scholars worldwide by Scholar GP 2020. We are extremely fortunate to have Professor Gautam with us, and we look forward to his valuable insight. Please join me in welcoming him onto Professor Brahmachari.
Morning to everybody. Here, elaborate introduction. First of all, I am very much fortunate to present aware childhood time. Fortunate enough my dear beloved students, scholars, dear colleagues, faculty members, my very respected Vice Chancellors and friends. So, today's topics I will discuss little bit on the electrochemistry. That is electrochemistry that has come forward and part of tools utilized in as Rajni Madam they acted on the all respect survival. So, practices or pioneering advances in chemistry are really directed towards its future. That is on which we are much for our own. The ultimate motto of the chemical fraternity is directly linked with particular. As far as the chemical fraternity is concerned, one of the most important part of their concern is to care or synthesize organic compounds and materials and their processes, obviously, on which the material basis of our sustainable society largely dependent. Hence, designing, innovation, and development of chemical processes must or should have to follow certain principles that make them conducive to life. Actually, first of all, what is sustainability and practice of organic chemistry? As you all know, that sustainability is a term that always stimulates one in taking every and the future in mind, right? In this particular fashion, and practice of organic chemistry, as you know, in the past, so the advent of concept of green chemistry as proposed by Professor Paul Anastas and John Werner in the year 1998, the whole theme has been changed totally. There are so many principles of green chemistry, as you know, dear students, and it is just celebrating its 25th year. It is very young and so energetic and so fast, and already developed as a distinct discipline within the organic chemistry and engineering. So you know about the principles of green chemistry, but these are the basic tenets. These are the basic tenets of green chemistry, and how a particular process mount a particular in determined by evaluating certain matrices called the green matrices, and that the matrices based on which we can say how a particular process is. So, organic chemist, and not only the organic chemist, chemists in general, engineers, chemical engineers, are very much optimistic, design and develop and practice green chemistry for a sustainable. So worldwide, for the students, this is a slide. Nature, you know, is carrying out, performing numerous number of chemical transformations each and every time. You know, is there any relation between green chemistry and the natural chemistry? Obviously, both are the same. Nature conducts each and every chemical reactions in a very conducive way. This is one of the examples, the most well-known example of photosynthesis, you know. The plant takes up carbon dioxide from the air, water from the ground, and by means of utilizing the sunlight as a chemical energy by utilizing recyclable photocatalyst or photosynthesizer, as you know, the chlorophyll, and transforming these reactants into the glucose, our primary source of energy, and oxygen that we take up for our metabolic pathway, metabolic reaction. So this is the most well-known examples of green reactions. And you can see here, from nature we learn that, what we can learn from nature. I summarize here that it uses of reactants that are non-hazardous and easily available. Generation of products you see that are non-toxic and useful. Use of solvents that are environmentally friendly. Use of catalysts that are non-toxic, inexpensive and reusable. Use of abundant sunlight and reactions occurring at ambient conditions, and generation of no. The ideal examples of green reactions. So the chemists are trying to mimic the natural processes, but to mimic the natural processes in toto, not an easy task. So as far as it can be, it can be mimicking better, and how much we mimicked the natural chemistry is certain by the matrices, as I mentioned. So can I go ahead? Okay, I am audible? I feel a little bit, okay. So we have been engaged in doing some research in the field of green chemistry, part of our various activities, and these are some of the selected publications in the last 5 years in the domain of green. And that is there. Okay. So I think that energy is a prime issue when we consider various green aspects. My own opinion, energy is prime one, because we can minimize the energy requirement. We can attend any green aspects particularly. So there are certain green tools, that the green tools, green energy tools, I may say, for preventing certain reactions, and these are the green tools. The use of ultrasonications, you know, microwave irradiations, high pressure, and recent times utilization of the visible light, utilizing commercially available LED lights, and mechanical grinding, that is the uses of ball mill machines, high-speed ball mill machines, and in recent times applications of electrochemical cells in implementing the organic transformation. But in my own opinion, if one can innovate, design and develop methodologies that are applicable using just ambient temperature and pressure, I may say it, room temperature organic synthesis, very elegant one. So I am giving a glimpse before coming into the topic, glimpse of certain selected examples. So from our laboratory, you can see that these are the room temperature based organic synthesis. And you can see here that in most of the cases, you do not need any catalyst or additive. Simple mechanism only based on the designing of the substrates molecule. So this is some of the glimpse of carrying out the organic transformations using the ultrasonic. Very simple method that has been quoted, and I'm giving you the to give you an idea how we can design your own course of. So this is the examples of some recently reported mechanochemical reactions utilizing high-speed ball mill as the high-speed mechanochemical energy, developing the energy. So these are involving the click reactions and CH functionalization reactions can be taken place very smoothly, very good to excellent. These are very recent examples. Visible light driven organic synthesis and involving rearrangement type of reactions and functionalization of type of reactions, being new series of organic molecules, not only new series of, as you know, that light catalyzed reactions of these new bond breaking processes. So for the experts, I can mention here 3 books by me. Visible light organic synthesis, just for with a foreword by Professor Ackerman, and this is catalyst-free organic synthesis from Rolls Institute of Chemistry, 2029, and this is the room temperature organic in academic press. Here I tried to discuss possibilities for the newcomers in this particular domain, how to design and develop problems. So let us come to my today's talk on organic electrosynthesis. So as you know that organic electrochemistry has already led in boom new synthetic methods, their mechanistic understanding, because due to its low energy consumption, mildness and environmental friendliness. So electrosynthesis has already led to several unprecedented methods. Much of the promise of such a technique is their ability to achieve unique bond constructions that are not feasible by some conventional methods. That's very important. And electrochemistry's unique ability to generate highly reactive radical and radical ion intermediates controlled fashion under the mild conditions required the development of several new electrochemistry getting valuable chemistry. Spectacular field of real truth scenario. Here is some selected cell-driven organic. You can see here you can see here that it is the warfarin analog, just simple one-step process of CsP3H functionalization giving you CO bond. Very interesting. And as in this is the enazyme scaffold, biologically much active scaffold that has been sp2 functionalization giving you organosulfur and organosulfur by electrochemistry. And particular scaffold is amino naphthaquinone, that is hydroxy naphthaquinone, much known biological lausan, that is in a plant, it is in a leaf, so it is biologically active and it's up to inhibited several biological activities. And with the help of electrochemical synthesis, you can also functionalize the sp2H with alpha hydroxide. So, this is formation of 3-nitro 2-aryl imidazo 1,2-A. Yes, that is, you know how much important this particular, and it is just electro rearranged functionalization and rearrangement, giving you 2,2-disubstituted benzopyranone, 2-hydroxy version of 2,2-disubstituted benzopyranone. This is the first report actually in the chemical synthesis. It is present in nature. I take this opportunity to discuss elaborately on two such schemes. Recently reported, 2024, we reported this scheme. So the first one, the electro-rearranged difunctionalization of 4-hydroxy alpha benzopyrone. Dear students, you see that these are some of the examples of natural benzo 2,2-disubstituted benzopyranones having multifaceted biological and pharmaceuticals applications. However, before this particular report, there is no such report for the laboratory synthesis of 2-hydroxy analog of this particular scaffold, and this is we first reported this visible light induced photochemical transformations. But this particular transformation suffers from little a number of shortcomings, like narrow substrate scopes, larger reaction time up to 20 hours, and non-scalability. That's why we have been motivated to design an alternative pathway, and we envision that electrochemistry may give an alternative pathway for this particular transformation. So you see here, very easy, the reactant, that is 4-hydroxycoumarines derivative, coumarine derivatives and alcohol. When you go for constant current electrolysis, CCE, the technique is known, in an undivided cell containing platinum plates at both anode and cathode in acetonitrile solution using lithium difluorooxalatoborate as an electrolyte, you passing just 12 milliampere of direct current, DC current, your 4-hydroxycoumarine undergoes electro-rearrangement, giving you the product, and you can see here that we, using this simple technique, you can able to synthesize a huge number of compounds, new series of compounds, that is 55 examples we synthesized in this particular method. And you note that the advantages, the difference between the photochemical and electrochemical process is that this is broad substrate scope, shorter reaction time, only within 6 hours it will complete it, and obviously it is scalable and more energy efficient, obviously. So these are the trial reactions we carried out to arrive at the best suited optimum reaction conditions by varying different types of electrolytes and their concentrations, electrodes, nature of electrodes, atmosphere, that is nitrogen, oxygen and other atmospheres, and we arrived at the particular conditions. So look at the variations, the scope, substrate scopes of the reactions. You see here that we actually used commercially available 4-hydroxycoumarines having substituents both electron donating and electron withdrawing at the benzene ring, and primarily these reactions is applicable for aliphatic alcohols, huge types of aliphatic alcohols, long chain aliphatic alcohol, branched chain aliphatic alcohol, cyclic aliphatic alcohols, and you see the corresponding yield, their time, and calculated Faraday per mole. How much energy is required for a particular transformation that has been reflected from the Faraday per mole. And you see the variations, various types of variation, including fluorine. You know that biologically fluorine and fluorine derived has enhanced the biological profile of a particular drug molecule. So now we checked the scalability of these reactions, and for this particular purpose we took 3 examples for larger scale synthesis, and in 3 cases, each and every cases, the percentage, yield percentage and time almost same. Here you can see, obviously you noted that the aerial oxygen, that is oxygen, molecular oxygen is inserted within the molecule, that is the carbonyl oxygen of the ester group coming from the molecular oxygen. And we used here the same cell, same vessel, same cell area, and 6-fold enhancement was possible, but I am confident that if we enhance the vessels and enhance the area of the electrochemical plate, the electrodes, this reaction can be applicable to further larger scale enhancement. So now, being an organic chemist, we always try to look at the mechanistic aspects of the reactions, and for this purpose we carried out certain control experiment, and these are the control experiments with radical and scavengers and singlet oxygen scavengers. You note that all the radical scavengers inhibited the reactions, indicating the involvement of a radical pathway by the during the reaction process. And DAPCO and triethylamine is a very well-known singlet oxygen scavengers. So they also inhibit the reactions, suggesting that the molecular oxygen, that is triplet oxygen, as we are using during the reaction vessels, is being transformed into singlet state during the reaction process. So from we actually come to know this type of reactions, and now we assumed what types of radicals can be formed from the starting compound, and we proposed our radical, and we proposed the adduct, what type of adduct can be formed, and we were delighted to detect all these radical adduct by means of high resolution mass spectroscopy studies. Also DAPCO adduct from the singlet oxygen also detected from the HRMS studies. So then we to eliminate the proposition whether the oxygen is coming from any water remaining from the reaction mixtures, we carried out a control experiment with in presence of water, and we see that no reaction took place. That means presence of water inhibited the reactions. That is, we are eliminating the proposition of coming the oxygen from water, if any, from the reaction mixture. And to establish the effect of the 4-hydroxy group has any impact, yes. When we carried out the reactions with simple coumarin, no reaction took place. Therefore, indicating that the 4-hydroxy group of the coumarin moiety plays some vital role in implementing the reaction. So from our isotopic leveling, the OH hydrogen is deuterated and is retained within the product, and it just changes its position from 4 position to 2-hydroxy position. This is our generalization. And when we took the cyclic voltammetry parameters or properties of starting compounds, these are the CV graphs. You see that 4-hydroxycoumarin did not show any oxidation potential, oxidation peak in the cyclic voltammetry, whereas methanol, as our model alcohol, just shows one oxidation peak at minus minus 0.52 volt. So based on all these things, we propose this mechanistic aspect, a new type of mechanism. You see that we propose alcohol, first of all, gets oxidized by single electron transfer, giving rise to alcohol radical cation 2 dash. And your coumarin moiety that undergoes tautomerization in the reaction mixture in the solvent, and 1 to 1 dash. And this olefinic enolic bond undergoes homolytic cleavage, giving rise to diradical 13. And this diradical 13 is trapped by BST as detected from HRMS. In course, it 2 dash and 13 undergoes heteroradical coupling, giving rise to adduct and eliminating 1 proton. And that proton is reduced at the cathode, giving rise to evolving out the hydrogen gas, molecular hydrogen. And we propose for the first time that triplet oxygen gets oxidized at the anode, giving rise to triplet oxygen radical that takes up a proton, an electron at the cathode, giving rise to molecular oxygen with a change in spin state. I did not find any literature previously, but we from our own experimental observation, we proposed that change of the spin state occurred somehow in this particular fashion, and we detected the singlet oxygen. And this now the singlet oxygen and radical species 15 undergoes intramolecular and homo and hetero coupling, giving you the intermediate 16 that collapses to the product and giving you a OH radical, OH dot radical that collapses into hydrogen and oxygen. These are our mechanistic propositions from observations of the control experiments and CV analysis. So you see that these particular methods, some major advantages are there. It is an electro-rearranged difunctionalization involving introductions of singlet oxygen insertion at ambient temperature, good to excellent yields, eco-friendliness, and you see that we isolated up to 87% yield with 55 examples, and most of them are new compounds. We just synthesized photochemically only 15 compounds. So these are the major advantages of these particular reactions. And the second one, how much time I have? How much time I have? 5 minutes or 7 minutes, okay? 10 minutes, okay. I will finish within 10 minutes. So this is the electrochemical synthetic approach for imidazo 1,2 pyrimidine. Imidazo 1,2 pyrimidines, you know, is very important molecule. These are some of the examples of biologically active imidazo 1,2 pyrimidines. And in the right hand side, you see the drug molecules, marketed drugs that involve this particular scaffold. Therefore, chemists are very much energetic to develop so many processes for 1,2 imidazo 1,2 pyrimidines. So we turned our attention only to the 3-nitro derivative of this particular scaffold, and we see that these are the previous methods for 3-nitro imidazo 1,2 pyrimidines. And you see the involvement of transition metals like gold, aluminium, external oxidants like iodine, TBHP, toxic solvents, heating, and long reaction time up to 20 hours. And these made us some energy to develop certain electrochemical, whether it can be done by electrochemical process, giving some benefits towards the green chemistry. And you see that very simple, beta nitrostyrene you can synthesize in the laboratory from aldehyde and nitromethane. And this is the commercially available 2-aminopyridines. When 2-aminopyridines and meta-nitrostyrenes are electrolyzed in DMSO using potassium iodide as the electrolyte, undivided cell, carbon and platinum, carbon anode, platinum cathode, just passing 6 milliampere of current, direct current, you will get the product at room temperature. And you see that it is a metal free synthesis, larger scale synthetic applicability, no heating, good to excellent yield, no external oxidants you are using, shorter reaction times, only 0.75 to 4 hours it is completed, broad substrate scope, and it is operational simple, very simple and practical one. So these are the trial reactions based on which we arrived at our optimum reaction conditions. And first of all, we go to see the mechanistic aspects of this reaction. And this is the experiments with radical scavengers and iodine trapping agent. Most importantly, sodium thiosulfate, when used, the reaction inhibited, thereby indicating that, dear student, in any situations during the reaction time, molecular iodine is being formed. That's why the reaction inhibited. So radical scavengers inhibited the reactions. So we detected, not isolated, the proposed radicals and their respective adducts by the radical scavengers, BHT and TEMPO, by HRMS spectroscopy studies. And here you see the cyclic voltammetry studies. Beta nitrostyrene did not show any oxidation peak. 2-aminopyridine shows only one oxidation peak, whereas potassium iodide dual oxidation peak. So based on that, we propose that, first of all, 2-aminopyridine gets oxidized by 1 electron at the anode surface, giving you that particular 2' radical amino radical cation that is trapped by TEMPO and BHT and detected by HRMS, which then regioselectively attack the alpha carbon of the olefinic double bond, and a proton is eliminated, that is eliminated at molecular hydrogen at the cathode surface, giving you the adduct 10. Now iodide is oxidized to iodine radical. Iodine radical can form molecular iodine, obviously. And then now the attack of the carbon radical, iodine radical, that is iodination process take place. And you see that adduct 10, we detected it by TEMPO and BHT adduct by HRMS. And iodination, you have the iodo product 11. And the iodo product then undergoes intramolecular cyclizations following Baldwin's rules, 5x rotate process, energetically favorable, giving you the intermediate that undergoes oxidative aromatization in presence of molecular iodine. So molecular iodine has some role here. So we see that molecular iodine is formed during the reaction time. So why the reaction cannot be done in presence of molecular iodine and DMSO? It is very logical, na? So that's why we tested the reaction under a ball mill, under mechanochemical grinding, and we see, yes, the reaction took place very efficiently and most efficiently, most fast than the electrochemical process, because a high energy mechanochemical process, it is a high and it is fast, obviously fast. So we arrived at this particular, and this is our mechanochemical strategy. Nothing else in a volume, in a container. It is available with the machine. It is a high-end rich machine, PM100. So the reactants, when ball milled in presence of basic alumina as a surface, because it is a 0.3 millimolar reaction, surface is needed for grinding, in presence of 0.5 equivalent of iodine and DMSO 0.4 ml, only little amount of DMSO is added with 7 stainless steel balls at 550 RPM, you will get the product within 35 to 45 minutes. Your reactions rate has been increased. So here we developed, here also the mechanistic aspect we studied in a very conventional way, and here is the mechanism for this particular transformations, ball milling transformations. You see that iodine first gives you the iodine radical. One iodine radical snatches one H atom, giving rise to eliminating one molecule of HA and this particular amino radical 2 dash. This amino radical has been trapped by TEMPO and BHT and we detect it. This amino radical then undergoes reduce-selective attack at the alpha carbon of beta nitrostyrene 1, giving you the adduct 10. This is also detected. And this adduct 10 now undergoes iodination reaction, giving you the iodo product. And this iodo product gives you the intermediate 12 that undergoes aromatization, giving you the final desired product. And we suppose that the HI as being eliminated reacts with alumina under the ball milling condition, the iodine is again regenerated. So we developed two methods simultaneously for this particular conversion. One is ball milling, that is mechanochemistry, and the other is electrochemistry. And here we synthesize so many compounds, and you can see the method A, that is electrochemistry, method B, that is mechanochemistry. These are the corresponding yields and their times. These are the products and the variety. And obviously, for larger scale synthesis, you see that we carried out the larger scale synthesis for electrochemistry as well as mechanochemistry, and under the same conditions without enhancing the electrode size. If you ask me which method is more eco-friendly, I may say it that mechanochemical ball milling is more eco-friendly because it needs minimum amount of solvent, DMSO, only 0.4 ml. So in terms of solvent using, it is more eco-friendly, and obviously it is fast. Within 45 minutes, the reaction completed rather than 4 hours. So for larger scale synthesis, mechanochemistry will be more better option for this particular transformations. And since we are the organic chemist, we obtained nitro, then we reduced the nitro into amino so that the amino version can be used as a synthon. These are selected examples here. So these are some of the documented advances of this particular reactions. So in summary, I'm finishing. The recent past has brought significant growth and attention towards applications of electrosynthesis in organic synthesis. And such advancement have been prompted by increased recognition of electrochemistry's ability to harness what I am saying electrical current as an imaginary reagent to facilitate a range of single electron oxidation reduction events. Electrosynthesis strategies thus have emerged as an effective green tool to design new and alternative synthetic protocols for diverse ranges of organic small molecules of promising medicinal and material applications. Electrosynthesis offers new chemistries and unprecedented mechanistic aspects for organic transformations, which boost the understanding of advanced reaction mechanisms of electrosynthetic organic reactions. Applications of electrocatalytic methods for the late stage functionalizations of complex bioactive molecules, with very important subject. And this somewhat new area in modern organic synthesis demands its exploration and applications in academia and industry for a sustainable future. And we anticipate that future development in the field of electrosynthesis or electrocatalysis will power the discovery of new reaction strategies needed to solve key challenges in contemporary organic synthesis. Even with this advancement, we expect that electrocatalysis will continue to expand into new chemical spaces to address pressing challenges of efficiency and sustainability encountered in organic synthesis. That is very important. So this time of acknowledgement, I am very much obliged to my own department for infrastructural facilities and the funding bodies. And obviously, my students, my former PhD students and current PhD students were the key player in this particular domain. I take this opportunity for the experts to present some of the recently published books in the domain of green and sustainable chemistry and organic synthesis. And since one of my active areas is natural products chemistry and medicinal chemistry, these are some of the books in this particular domain, natural products and medicinal chemistry. You can consult it. And finally, I'm thankful to you all for your kind patience and kind hearing. And I welcome you all at my own ashrama that is founded by Rabindranath Tagore. That is also a very peaceful place. Thank you all for your kind.
In the interest of time, we'll just take 2 questions from the audience. If anybody has any question.
Is there any questions from the students? One question.
Saram sir, thank you for coming here and taking your time. It was a very wonderful presentation. I had one doubt that is there any limitation of doing a organic synthesis via electrochemical reaction? Once the reaction is done, have the product, how can we recover the product? Like how can,
What I understand, your question is whether electrochemistry is applicable for all reactions. The answer is it is under investigations. You have to try whether your particular reaction should go by electrochemistry or not. That's one thing. That's why research is very necessary. And secondly, it is a technical issue how you will isolate the workup of the product. It is a specific practices there for workup your own product. So it differs from reaction to reactions. Actually, it is standard protocol as maintained by the organic chemist for isolating the product. You isolating the product and you go for column for purifications in case of electrochemistry. But in case of mechanochemistry, in certain situations, you may, as per own experience, in many reactions, you do not need the column category purification. Simple filtrations can give the pure products. If you go the publications, you will see the details, or in the supplementary, you can read all details as I indicated here. And you may also interact me during the lunch time or time for more information. Okay, Professor. So I'll be very happy because I'm a teacher, na? So I basically I wish to interact with my students. Everywhere is students are students. So any more questions from the student? Yes.
Namaskar, sir. Thanks for taking your time out. Just had one doubt. Means when we say green chemistry, the first very large-scale idea which got global recognition was something like click chemistry, which came, let us say, in 2001, and by the time it had practical utility, it was almost 2010. Now that, let us say, mechanochemistry or electrosynthesis is just getting started, how much time do you think would it take for the industry to be ready to apply these processes? And sir, just as a follow-up, mechanochemistry, how safe is it when we do it in the large scale? Has it already been done? Because something like ball milling, doing it in a large scale is, means I personally can't visualize it being very safe for the workers.
Very good questions. Please take your seat. As far as the mechanochemistry is concerned, as far as I know, it is industrially applicable in Germany. So in Germany, there are so many industry installment of large scale and high voluminous mechanochemistry. So it is an established fact that ball milling machine is now being used in industry, particularly in the Germany, as far as my information is concerned. So I think there is no much hurdles to run the ball mill machine. It is very easy. The students can run. It is very safe, and with all types of safety aspects is there. So there is no chance of burst out or something like that. But before prescribing whether it is applicable to large-scale synthesis or not, large-scale synthesis means we have to say kilogram level of synthesis or quintal level of synthesis, that different thing. So for that particular systems, we are carrying out a reaction laboratory. Gram scale synthesis we are doing. But when we are going for kilogram levels or quintal levels, then our chemical engineers are there. They will design the applied field in which type of mechanochemical design will be required. And that's not the task of organic chemists, it's the task of the chemical engineers to develop such type of machines. And as far as I'm concerned, there are so many machines available industrially in the Germany. And as far as the electrochemistry is concerned, so I think it has a very, very good prospect in industry. If we design the parameters for larger scale synthesis, the electrode size, area, the current flow, everything is to be determined for large scale synthesis. And that tasks are the tasks of the engineers. But it's a very good prospect. Because in two reasons, it will be installed industrially, and it will give you new products with new chemistries. That's very important.
We thank Professor Gautam Brahmachari for highlighting the basic tenets of green chemistry, bringing out green matrix optimization approaches in organic synthesis through electrosynthesis, overcoming challenges of energy efficiency, non-scalability, and long reaction times with illustrated examples. We witnessed the dexterous maneuvering of organic synthesis leading to desired products utilizing green methods, which is the core of principles for sustainability. We now request our Honorable Vice Chancellor, sir, to kindly offer a token of love to Professor Gautam Brahmachari. Sai-Ram. Thank you, sir. The second speaker for this morning's technical session is Professor K.R.S. Chandrakumar, Scientist G, Baba Atomic Research Center, Department of Atomic Energy, Homi Baba National Institute, Mumbai, Maharashtra. Professor Chandrakumar will be addressing us on the topic, Chemical Concepts and their Role in Designing Nanomaterials for Energy and Environmental Applications. We request our student Harishi Narayanan to introduce and invite Professor Chandrakumar. Sai-Ram.
Om Shri Sai Ram. It is my pleasure to introduce the second speaker of day 1 of the symposium, Professor K.R.S. Chandrakumar. Professor Chandrakumar is a distinguished scientific officer at the Baba Atomic Research Center, Mumbai. Sir completed his PhD from the prestigious National Chemical Laboratory in Pune. Over the years, he has made significant contributions to the areas of chemical reactivity descriptors, the development of hydrogen storage materials, and the study of structure reactivity relationships in carbon-based nanostructured materials. Professor Chandrakumar's research spans several innovative fields, including the creation of nanostructured materials aimed at solving energy and environmental challenges, investigating the fundamental mechanisms behind complex nanostructures like DNA origami, and studying the growth mechanisms of carbon nanotubes and fullerenes. Additionally, he is engaged in computational modeling of protein structures and understanding the chemistry involved in the ripening process of plants. With numerous publications to his credit, Sir's contributions have significantly advanced these areas of scientific inquiry. Alongside his research, Professor Chandrakumar is deeply committed to promoting science and supporting fundamental education initiatives. He also serves as a visiting faculty at the Center for Excellence in Basic Sciences, University of Mumbai. Professor Chandrakumar's outstanding contributions have earned him several prestigious awards. To name a few, Sir received the Young Scientist Award from the Indian Science Congress Association in 2002, the Young Scientist Medal from the Indian National Science Academy in 2005, and Young Scientist Award from Department of Atomic Energy in 2007. More recently, he was honored with the Scientific and Technical Excellence Award in 2015 and the Chemical Research Society of India Bronze Medal for the year 2023. We are incredibly fortunate to have Professor Chandrakumar with us today, and we look forward to hearing more about his fascinating work. Please join me in welcoming Professor K.R.S. Chandrakumar.
Okay, thank you, ma'am, for your kind words. And I feel very honored to be here in such wonderful place. This is my first visit here, and I don't know what to say in the service kind of motive this institute is running. And henceforth, any program is there, please do not welcome me or send any invitation. Just send me the things. I will be here. And yesterday, when I talked with the organizer, and they told me that this conference is meant for the research scholars and postgraduate teachers and postgraduate students. And hence my talk, I have introduced some of the basic and then some of the research topics. So both the things are covered. And at the outset, I would like to thank the organizers, head of the department, and Pratyusha ma'am, and everyone for your kind invitation. And let me just go through the journey in the field of theoretical chemistry to propose some of the useful materials for energy and environmental applications. Well, before I go through the research topic, I will just introduce you what is meant by theoretical or computational chemistry. The theoretical chemistry is nothing but the mathematical description of systems of chemical species, and we use only the computer to solve the chemical problems. And we simulate the chemical structures based on the structure and its properties. And mainly it focuses on the fundamental laws of physics, that is the quantum mechanics. And the chemical phenomena or chemical processes that we do, everything has been done by the computers and based on the fundamental laws of physics. That is the first point. And the modeling can be done. The modeling can be done for quantitative measure of the important parameters. Chemistry as such deals with the many fundamental properties like investigating the properties of molecules, how a reaction proceeds, and what is its mechanism. And finally, you need to find out the heat of formation, heat of reaction, reaction rate constant, and transport properties. Everything can be done by this theoretical chemistry if you have a proper model in your system. So, and in nutshell, it provides valuable insights into the properties of new materials and efficient design of new products at the macro level. So basically, it gives you the fundamental insights and through which you can actually propose the new materials. And it basically it provides you guiding principles. Now, why chemical complexity happens? Why do we need such kind of thing? Like Professor Brahmachari, he mentioned, he has written a lot of books. Why do you need to write such books? And why do we need to have such elaborate experimental setups? Because chemistry is a very complex subject. There are some subjects which are very useful, but subjects are essential. That one of the essential subject is the chemistry. It is very complicated. Unless we go into the depth of the sea, we will not be able to know. And that kind of complexity is involved in chemistry. And for that, you need to have such kind of big community. And for that, experiments and the designing purposes. And look at this. The chemical reaction can occur in the lightning speed. And for that, do we have that experimental setup to investigate how the reaction is going on? No, we don't have it. And like this, many problems are there. For example, in terms of energy, how we can have any material that can be very useful to provide the hydrogen energy or any kind of energy in terms of ammonia production, that I will be talking about it. If we ask such questions, we don't have any proper answer. That is why in 1999, in the area of quantum chemistry, Nobel Prize was given for their fundamental contribution to the quantum in the field of quantum chemistry. And not only that, the application of quantum chemistry at the very basic level to the experimentalist. Even the experimentalist can now use this quantum chemical techniques to propose the mechanism and to study and propose a new molecules or materials. And this is the professor, Walter Kohn and John Popel, and both of them, they got the Nobel Prize for their development of computational methods in quantum chemistry. And more recently, one more Nobel Prize was given in the year 2013, and 3 people got it. And for the, it is here, Martin Karplus, Mitchell Levitt, R.A. Warshall, and they, in fact, they applied the quantum chemical techniques for exploring a macromolecular, for example, trying to understand the biological systems. And for that, they proposed different type of molecules. For example, designing new drugs or new material. Computational chemistry, how it allows for the prediction, that means accurate prediction of how small molecule will approach and bind to the proteins and surfaces. And to that extent, they have proposed the method and they were awarded the Nobel Prize. And the problem is that it has the 1,000 to 10,000 atoms in a protein, and doing such kind of calculation is extremely difficult. Okay, and for that, we need to have a proper method, and the method proposed by this Nobel laureates have been very vital for investigating the structure and function of bioactive molecules. Whether it is a coronavirus or drug design, it is now applicable. And the success and achievement of this method is enzyme catalysis, photobiological processes, electrostatics in energies in macromolecule, protein folding, development of force field, and more importantly, the industrial catalysis and drug discoveries. In fact, in India, the acceptance of quantum chemical methods or computational methods is very less in industrial level, but in abroad, this is contributing to the one of the important method for their drug discovery methods. Okay, so not only that, this year the Nobel Prize was given to the chemistry and physics in the field of artificial intelligence and machine learning, and the basics of these two methods come from this, the quantum chemical methods. So the basics comes from the quantum mechanics, and this is how we define. This is my God, that is a Hamiltonian, and the Hamiltonian, you all must have heard about it, and the kinetic energy operators, potential energy operators. This Hamiltonian is nothing but it gives you the energy. This is the operator that calculates the energy of the system. Like classical mechanics, we have the half mv square, and we have the kinetic energy parameters, and potential energy in classical mechanics, it can be like gravitational waves mgh or Coulombic energy, and here we have the similar operator here. That's all I needed. I need to define the Hamiltonian in this fashion, and next is the Born-Oppenheimer approximation, considering weight of the electrons and nuclei, they differ from 1000 units. So I freeze the nuclei and allow the electron to move, and that approximation is called as the Born-Oppenheimer approximation. And these are the methods that I will be using it. So you have now defined the Hamiltonian under the Born-Oppenheimer approximation. And how do we solve this equation? Basically, you start from Schrodinger equation, H psi is equal to E psi, and we have the Hartree-Fock theory, basic concepts. The Hartree-Fock theory is nothing but the mean field approximation. And it just approximates all the electrons, like in the ocean of the electron. You treat one liquid drop and then consider how does it interact with all other surrounding water molecules. In the similar fashion, the interaction has been accounted in this method, and we have several approximations. Based on that, we calculate the energy, and these are the corresponding equation for that. And here we have the term, Hamiltonian term, one particle system, and this is the Coulombic system. This is nothing but the how two electrons, how do they interact by the Coulombic forces. In the similar way, it is written here. And this is a classical part, and this is a quantum chemical part that comes from the quantum mechanical principle called the exchange part. So combining both the things, Coulombic and the exchange part and the one particle system, my Hamiltonian is defined. And you calculate the energy using the Hartree-Fock method in this pattern. And you will see that how one electron can move in presence of the other electron. Being two electrons are negatively charged, they try to repel each other. So one electron motion is actually correlated with the other electron. The electrons cannot move in the same direction. They have to move in the opposite direction. So the electron movement is actually correlated, and the correlated electrons, the energy comes from this pattern is called as the electron correlation. So any model that you develop, the electron correlation should be considered, and without that, the chemistry cannot be explained. So there are several methods that to take care of the electron correlation. For example, the Hartree-Fock method, Muller-Closet method, and these are the scaling behavior. And another method is called as the density functional theory. This has also got the Nobel Prize, and this comes from the Hohenberg-Kohn theorem. And using this, you can actually incorporate the electron correlation. The issues with this kind of different kind of methods come from the formal scaling. That means that the computational time. Although the method is very well known, and it is possible to evaluate the energy of the system or predict the new molecule for a specific application, but it has several limitations. It is not possible to to predict any kind of properties. The reason is that the computational power. If you have an excellent computer, may be possible to calculate any kind of predictions. However, if you have the limited capabilities, you have such kind of limitation. That is a n to the power 5, sorry, n to the power 7. So because of this brute force calculations, some limitation come, and now we ask the question, how do we overcome this limitation? And that is the essential part of this talk. So what we do is that we propose some new chemical concepts, and using these concepts, we try to come up with the proposal of new molecules or new material for a specific application. For example, you know, the chemistry is, it has come along with the human evolution. Nothing was there, fire. Now we know that it is a combustion process, and you know how it is complicated also, that I have already mentioned about it. Okay, so how do we understand the essential features of the complicated chemical phenomena? And hence we need to search for the conceptual models. The first question is that chemistry deals with the atoms, molecules, right? How do the molecules interact, and why do they interact? That is a primary question that we have. Is there any fundamental reason through which a molecule interacts with another molecule? This question was addressed by Professor Keiji Murakuma, and he said that in terms of orbital overlap and the origin of donor acceptor complexes and hydrogen bonding and proton affinity, based on these concepts, the basic nature of the molecular interaction has been explained. And our next question is that in the given group of atoms in the course of molecular formation, is there any geometric pattern? And this is proposed by Professor Dev, one of the most astounding theoretical chemists. The present generation is all follows his group, and he proposed that simple mechanical model for molecular geometry based on Hellman-Feynman theorem. And he used the force concept to describe the structure of the molecule. These are the concepts. Now, next question is that obvious question, and the most important question is that what kind of molecule can interact with another molecule, right? That's what we want to know. And this is what we have, the Pearson's hot-soft SSAB principle. Like this is now textbook material, right? So it says that if you have the soft or hot acid, it reacts faster and forms a strong bond with the soft and hot bases, right? One of the most celebrated SSAB principle. See, a small concept and written in 4 words, and that has explained most of the chemistry. That is the beauty of the concepts. And another Nobel Prize concepts, when 2 species approach each other in the course of the reaction, how does the energy change? Energy species change. And this has been explained by the theory of homo-LUMO interaction called frontier molecular orbital theory. And Woodward, Hoffman, and Kenichi Fuki, these are the Nobel laureates, and they define that the frontier orbitals of any system that decides the most preferred direction of electron flow during a chemical reaction. Sorry. And these are the thing called as the conceptual chemical reactivity theory, and it unifies all the qualitative concepts within the theoretical framework of density functional theory. Now, the question that I ask here, can such qualitative concept be useful in designing molecules and materials? So far, the concepts have been applied to explain the observation, chemical observation or chemical interaction. Why the molecule is interacting with another molecule, and what is the possible reaction product, and how much product you can get it. The question here, what we ask here is that, can this concept be applied to predict the molecules and materials for some specific applications? So this is what I call it as a concept-aided search for materials with specific applications. And so in the present talk, I will focus on hydrogen generation and ammonia synthesis. So the first one, what I will be speaking is the hydrogen generation. As you all know, hydrogen is nothing but the alternative energy sources, because what we use is the fossil fuels. It's going to deplete in next 50 to 50 years, and we should look for another alternative fuel, and one of them is the hydrogen, other one is the nuclear energy, and that is where I come from, Baba Atomic Research Center, which focuses on the nuclear energy. And another alternative source is the hydrogen. Why is it so? If you take the coal, and per gram you get 29 kilojoule, and gasoline, diesel, you have this number. But look at the number for hydrogen. It is 120 kilojoule per gram that gives the energy. So hydrogen has the highest energy content per unit mass, and that is why it is considered to be one of the most useful source of energy. And nowadays we all now have come up. Now it has become not only the textbook material, like it is a newspaper material. It has become so common, the hydrogen that is using as the alternative energy source. Sorry, some problem is there. It has gone. Oh. Sorry for the interruption. Yes. Okay. What is the requirement for hydrogen storage material? Once we find the storage, now we need to think about how we can transport hydrogen. And the basic requirement is the appropriate thermodynamics, that is a favorable enthalpies, fast kinetics. Means when you want it, hydrogen should be liberated from the system and it should be able to release. And the capacity should be as high as possible, and it should have the high gravimetric and volumetric density also, and it should have the long cycle lifetime. So these are the primary requirement for having a hydrogen storage material. And the concept that we apply to propose the hydrogen storage material is based on the electrostatics, curvature of the material, aromaticity, and charge transfer. And let us see how this simple concept can be very useful to predict the hydrogen molecule interaction with the cation. You can see that this is the sodium ion and you have the 8 hydrogen molecule. If you have lithium, 1 ion can in fact interact with the 8 hydrogen molecules. And the best feature of these complexes is that it is non-dissociative, because hydrogen, you should get it as a hydrogen molecule. You should not get it like a hydrogen ion. That is the important one. If you have the alkali metal ion, you can have the non-dissociative and with weak interaction energy. With the small stimulus, if you just heat it, you should be able to get a hydrogen molecule. So that is why it should have the weak interaction energy. And here the interaction is driven by the electrostatic forces, and the basic mechanism is that hydrogen molecule doesn't have the dipole moment because it's a homonuclear diatomic molecule, and it has only the quadrupole moment, and with that quadrupole moment it interacts. So that is the mechanism. And this is a number of hydrogen molecule, how the interaction energy varies with respect to the number of hydrogen molecule, and you can see that it is within the range it comes under for the requirement of hydrogen storage materials. So if you have the positive ion, we have seen, and if you have the negative ion, what could happen? So similar electrostatic, because whether it is cation or anion, electrostatic forces will simply apply onto the system, and we indeed see that even the negative ion can simply absorb the hydrogen molecule. And if you have the halide ion or cation, if you have the system like this, 2 ions, and you can see that you can form a framework materials. Okay, so this is a theoretical prediction. Basic study has been established. Now, how do we go from the prediction to the actual visualization? And this is our proposal, that 1 ion, if it is sufficiently separated by around 4 angstrom, you can have the such framework material and you can apply it. And the next concept is the curvature. And the curvature I simply explain by this. We have the planar molecules, and with that planar molecules, the reactivity is very, very less. And the moment you introduce the curvature, means you slightly bend it, and you can see that the reactivity of such planar thing, it is very high. For example, if you have the graphite, it is nothing but the planar carbon sheets, and that is only the planar, and it is less reactive. But the moment you curve it and form the carbon nanotube or fullerene matrices, the reactivity, it increases. Now, why it increases? It is based on a simple reason that the curvature involved here, it is very high. It can be convex curvature or concave curvature. I will show you the material. Here, you see here it is a plane, okay? No curvature is involved, and sodium atom is coming nearby that. And you can see that there is no interaction here, no interaction at all. But the moment you bend it, means you slightly introduce the curvature, you can see that the sodium atom as such is interacting with the curved benzene effectively. And that shows the power of curvature. The reactivity, it increases abruptly the moment you increase the bending angle. Sorry. Now, the point here is that atom is approaching and automatically it is getting ionized. That is what we see here. So, charge and ion, the bending angle. So, as you bend it, like from 10 degree to 35 degree, you can see the charge on the sodium ion, it is increased from 0 to 0.6. This is one of the important results. And the interaction energy also. Initially it was 0, where there was no bending, and as you bend it, you look at it, the interaction energy is abruptly it is increased. Now sodium atom has become ionized, so these ions now can interact with the hydrogen molecule. Like this, planar, curve, and if you have the ion and the hydrogen molecule, it is easily interacting. However, if you have only lithium, if you allow the hydrogen molecule to interact, it will never interact because the lithium exists as atom but not charged ion. So to make it ion, we applied the curvature concept and you can get it. And this is what happened. You take any kind of fullerene materials, you can have the interaction with the alkali metal ions, and you can even explain why different type of fullerenes have different reactivity. And this says that because the different type of fullerenes, either you take the C20 or C60, C70, the intra and intercurvature values are very different. So the different fullerenes can have different reactivity. And this was published in Nanolater by using the simple concept, the curvature concept. And it explained what should be the optimum degree of curvature for a particular material to have a desired property. The fundamental problem that we have is how we can make the materials with desired property. We have explained in terms of the curvature. And now what we have done is only the theoretical prediction, and you can see that the Nanolaters in the same journal, people have experimentally they verified, and they said that lithium based fullerene can in fact interact with the hydrogen molecule. You can have 5-8% of hydrogen molecule. However, the requirement is lesser than 6%. So this shows the validity of our prediction for the hydrogen storage materials. Let me go to the another concept based on the charge surface and aromaticity. Now, I start from C4H4, C5H5, C6H6, C8H8. Okay, very simple. Here you can see that in C4H4, so once again the atom is allowed to interact, and you can see that benzene doesn't interact with the sodium atom, but C5H5 cyclopentadienyl ion is effectively interacting with the sodium atom. And you see the interaction energy is very less for hydrogen. However, C5H5 case, the interaction energy is extremely high. So this shows that minus 60 is the interaction energy value, and the sodium is having the 0.6 charge. This is what we have seen in the case of fullerene as well. And now you can see that the other system also, C8H5, and the second higher most system, 35 kilocal per mole. So why is it so? And now if you look at the structure of this molecule very carefully, this is already aromatic complex, and it doesn't allow any electron to go from its center, or it doesn't accept, or it doesn't give up. That is a benzene molecule character. But in C5H5 case, if it accepts one electron, it becomes aromatic in nature. And hence, this molecule is really looking for one electron, and that we are giving in terms of the sodium atom. The moment sodium atom comes very close to this molecule, the sodium atom gets ionized and it becomes aromaticity. So the role of aromaticity has been explained in designing these hydrogen molecules. The molecules to materials, how we can have it. Like you have the C5H5 case. Okay, if you have like this, you form the linker systems here, C2 system, and you can have the beautiful complex materials. And now this is called as the molecular organic framework material, where the organic molecule is only involved, and the if you allow the sodium atom or any alkali metal to be to place it on top of this, you can form the materials. So now let me just go to the another topic, that is for the environmental applications. For the CO oxidation problem, let me just see how this concept can be used. This is for the younger generation and students. You can see that the one molecule that which has the highest bond dissociation energy, which one can you tell? From this table you can see that that is a CO. And look at the bond dissociation energy. It is around 1047 kilojoules per mole. And look at the nitrogen molecule. The second highest dissociation energy is 942, and the third one CN bond and CC bond. So that is why dissociating CO molecule is extremely difficult, and you need a catalyst for that, either for CO molecule or nitrogen molecule. Nitrogen, I will come to that second part. I will be discussing about that. And now in this few slides, I will show you how one can dissociate this CO molecule. And you know what is the importance of CO molecule? It is one of the most environmental pollutant, and because of that we have several adverse effects in the environment, right? And you need a very expensive catalyst for dissociating this CO molecule, and you need a very high temperature and pressure. What our study says that if you have a nano-sized gold cluster, you can see that such molecule like CO, it interacts with the gold molecule with this highest interaction. That shows the beauty of this gold cluster. The gold cluster can interact with the CO molecule at room temperature. You don't need the high temperature or pressure. Even in the presence of just like room temperature, you can absorb the CO molecule and keep it. And not only, if you have different molecules, it can catalyze the CO into some other useful chemicals. So that is one of the advantages of having the gold cluster. For example, if you have the oxygen molecule nearby that, you can even allow it to interact with the gold cluster, and you can see that the next one, CO oxidation, it can, if you have oxygen molecule, the CO is converted into CO2, and further the CO2 is further converted into useful chemicals. So this is our logic. If you have CO molecule in atmosphere, we use the gold catalyst to convert it into CO2 in presence of oxygen molecule, and the barrier is significantly reduced. That is the beauty of the gold catalyst. It can do it at room temperature. You don't need any adverse condition having this type of thing. And now this has been verified for a number of complexes. And now we have gone into the nanobiohybrid materials also. For example, if you have the complex DNA-based gold nanocluster complex, this can also act like a potential catalyst agent. And for example, if you have the AU3 catalyst here, that is adenine and thymine, guanine and cytosine, if you allow the hydrogen molecule to interact, CO molecule to interact, it can even convert into CO into CO2 and CO2 to the useful other chemicals. This is for the tetrad unit of the guanine. So the basic idea here is that once again the electrostatic plays key role here. The charge present on the gold catalyst that actually attenuates the CO molecule for the initial activation and then further reaction proceeds. So this is our proposal, this one. And how do you generate the hydrogen molecule? Once again the same gold nanocluster has been used. That is a dissociation of water molecule on the pristine cluster, and this involves the barrier height of 2.04 electron volt. And if you have the carbon based nanocluster and the gold cluster is here, and you can see that the barrier is reduced by 50%, and that is done by the gold nanocluster. On if you put it on top of the or functionalize with the carbon nanomaterial, it can be either with the nanotube or the fullerene surface. And this is the reaction mechanism. We start from the water molecule, and you can see that the water molecule is interacting here. The oxygen is with the gold surface, and 2 hydrogen atoms is going away, and upon interaction with the one more water molecule, these 2 surfaces are the surface is enriched with the OH and hydrogen is coming out. So this is called a water splitting reaction. That is how to generate the hydrogen for alternative energy sources. So now let me go into the another concept that is called as a confinement. The confinement, how it can act like a catalyst. It can be even spatial or electronic effect. Excuse me, just a minute. What is meant by confinement? I have 5 more. Yes, yeah, okay. I'll finish it soon. The confinement effect is nothing but you go in the lift and you are surrounded by the 4 walls and you feel that you cannot be there for long, right? You start feeling uneasiness. So like this, you reduce the dimension. Like a lift, you just shrink the size of the lift and assume that you are at the molecular level, and the molecule starts feeling some kind of uneasiness, and this is called as the confinement. It's like a squeezing. The electrons which are surrounded by the atoms and molecule, they start behaving in a very different way, and that you need to capitalize. If you perturb such electronic density distribution, then you can achieve several other chemical reactions. Now we will see how we can apply this concept and achieve the most important reaction. Let me just go into the result part. One thing, here you just see here, water is frozen even at 138 degrees C. That means that we know that freezes at 0, but even if you increase the temperature inside the same water molecule, if it is inside the carbon nanotube, is frozen even at 138 degrees C. So you can imagine what could be the effect of the confinement. Okay, so certain unusual thing can happen. So these are the few things which are already there in the literature. You can have the diffusion of liquids, means you can enhance the diffusivity, and catalytic activity you can enhance, and the phase transition can also happen, and peptide denaturation. These are the effect of the confinement. Now I apply this concept for the formation of nitrogen hydrides, okay, from nitrogen. Well, this slide is one of the most fundamental slide, textbook material, and this slide is, the content is known in the literature for the last 120 years. It has got 3 Nobel Prizes. Imagine the complexity of the problem. And if you think about it, what is there in it? You have nitrogen molecule, hydrogen molecule, and you need to form ammonia. What is the big deal about it? That is why it has got 3 Nobel Prize. That is the beauty of this subject. It is not that easy to activate nitrogen molecule like carbon monoxide. It has a triple bond. The bond dissociation energy is once again nearly 980 kilojoule per mole. So, and another hard molecule is the hydrogen. That is also, it is not easy to dissociate. So that is why 2 dihard molecules you have, and you need to form the one of the most useful molecule, that is the ammonia. And probably you must be knowing, this is the second most important commodity economical wise in the world wise. After the next to the fuel, the ammonia is the only molecule is the requirement is so high that decides the economy of a country. So the ammonia molecule synthesis is extremely important problem in deciding the economy of a country and the important application in various fields. Ammonia forms a strong foundation in organic chemistry to inorganic chemistry. It is most important part of the farmers. It acts like a fertilizers. Ammonia molecule is useful for synthesizing the fertilizers. So that is why it has got such important nature. Unfortunately, we all rely on only one process, that is the Haber-Bosch process. And 120 years old technology, still we follow it. And we are chemists, we haven't come forward any other alternative method other than this Haber-Bosch process. So the important question is that, can we have another process? May not be equivalent to Haber-Bosch process, but can we achieve the ammonia synthesis? That is what we have made an attempt, and this I have explained here. See here, the Haber-Bosch process is the energy intensive process. It almost 1% of the energy produced globally. That is, and it pollutes the environment by 12%. A single molecule can cause the environmental pollution by 12% annually. So that is why the Haber process is one of the important process, but we have to accept its side effect. It's a 12% environmental pollution, and it consumes 1% of the energy. Globally, what is produced? Although the number looks 1%, very simple number, but it's a huge amount of energy is involved. Now, you see here, you have nitrogen and hydrogen. We just increase the proportionally the number of hydrogen molecule, and you can see that the product that is formed, if you confine the nitrogen and hydrogen molecule, and if you have the less number of hydrogen molecule, no reaction is happening. The moment you increase from 2 hydrogen molecule, 3 hydrogen molecule, we start forming the hydrazine N2H4, and if you increase further the hydrogen molecule, you form the N2H6, that is the dimer of ammonia molecule. Okay, and you can see that the nitrogen distance here 1.1, that is in nitrogen molecule, and the moment it forms ammonia, you can see that it has gone up to 1.4. 1.4, it is already dissociated, and it is with the hydrogen distance you just see here 1.048, and the typical hydrogen bond length is the 1 angstrom. And you can beautifully see here is that the NH bond is already formed, and it forms the bond angle also. NH3 molecule is sp3 hybridized, and it should have the similar thing, like it can vary from 105 to 110, and exactly it is forming. So this shows that without going to the elaborate of confinement effect, I just want to show you that the confinement can cause the formation of nitrogen hydrides starting from hydrazine and ammonia. Here you can see the average coordination number of nitrogen molecule. Initially it is 0. Coordination 0 means no reaction is initiated. Nitrogen is existing as nitrogen. But the moment confinement is introduced and the time is in femtoseconds, you see that the coordination number is increasing. It is increasing means the nitrogen-hydrogen bond started forming. Here, 1, 2, 3, 4, 5, 6. You have 2 nitrogen atoms. Correspondingly, you have 6 coordination. That is a NH3 dimer. And you can see here, NH3 dimer is formed here. So, so the coordination number increases systematically from this. And NN bond length variation, this is the nitrogen initially equilibrium bond length. And as the hydrogen starts interacting, slowly the nitrogen-nitrogen bond length elongates, right? And it starts from 1 angstrom, 1.1, 1.2, and it saturates at 1.5 angstrom. And the ammonia dimer is already formed. Well, this is a structure. You can see that. And not only that, you can have the cucurbityrol or zeolite also. The nitrogen hydrates formation is established by our work. And so, how these chemical reactions are happening under confinement? That is a question we ask. And the answer that we have is the experiencing high pressure is the triggering factor. Now, you calculate the pressure, we calculated, and you can see that as the cavity sizes increase from 4 angstrom to 10 angstrom, you can see that the pressure is dropping significantly, right? Exponentially decays, and smaller the cavity size, the pressure is very high. So this is what is meant by the uneasiness felt by the nitrogen molecule, okay? And under this region, the reaction is happening. This region, not here. If you go beyond 7 angstrom or 8 angstrom, nothing happens. So the required pressure is the gigapascal, and experimentally it is very difficult to achieve. But if you put it under confinement, this reaction becomes feasible. And Haber-Bosch process is happening at 20 megapascal, okay, for your information. And what we predict through the confinement, it can go very easily. And the important another fact is that we don't use any catalyst. Haber-Bosch process, the catalyst is involved. That is why you need to have the high temperature and high pressure to activate the catalyst. But here, no catalyst is involved. Well, you all must be knowing Roald Hoffmann, and he established the concept of chemical imagination at work in very tight places. And you can see that if you increase the pressure, this is a lady's shoes, right? It creates 0.01 gigapascal, simple shoes, right? And like this, we have a different type of application, and through which you can go up to 1000 gigapascal. And at each level of pressure, you can have a different type of chemical and physical processes. This you can refer in the Anglo Chemistry paper. One of the most beautiful paper he explained in a very simple language, the Nobel laureate Roald Hoffmann. This we published, the exemplary nano confinement for the proton transfer. And so to conclude, if you have a conducive atmosphere with suitable cavity, you can have some unusual chemical reactions, and that can be done by the confinement. Okay, and we also propose several chemical concepts to predict and explain how we can form different type of material for specific applications. All right. Finally, I acknowledge my colleagues, Ms. Karunya Devi and Dr. Manoj Tripathi and the BRC Computer Center for providing the high performance computing facility. And thank you all. Yeah.
Sir, thank you for your presentation. I have two questions. Regarding the curvature effect that you have discussed about how it increases the reactivity of a substance, what type of molecular reactions are the most reactive for this curvature effect? And can we direct the movement of molecules as desired with the help of this curvature effect?
Okay, yes, it's a good question. The basic idea here is that how to make the surface very reactive. Okay, so based on your requirement, you can have a different type of applications. So the moment surface becomes active, you can actually make the molecules to interact with its surface, whether it is a physics option or chemist option. So initially it won't be reactive at all. Okay, so but the same surface, if you want to make it active, just introduce the curvature, means take a different type of molecules which has a curvature type, and then automatically you will see that because of the curvature, reactivity is increased and the molecule can now absorb on the surface, and through that several reactions can take place. So one of the application that I have shown here is a hydrogen storage. Like this, you can also have some catalytic purpose also, which is yet to be explored. So you can also do it. That one. Yes.
Sairam sir, thank you for the presentation. Even at the undergraduate level, we learned a lot. So
Thank you.
My question is regarding the carbon nanotubes. Sir mentioned that water remains frozen even at temperatures as high as 130 degrees Celsius. And I find that very fascinating. So what exactly are the interactions? What makes carbon nanotubes so magical? Because even in synthesis of ammonia, sir mentioned that in the carbon nanotubes, the coordination number increases quickly. So what is so magical about carbon nanotubes, sir, chemically?
Well, this is yet to be answered, frankly speaking. I know the chemical process, what is going on, and the intricate details about the confinement effect is to be explored. But to my knowledge, what we have explained is that under confinement, the pressure increases exponentially. That's what in the last slide I showed. If you increase the pressure of any system, tremendously, means right now we have the Pascal level, and you go to the gigapascal level, and under that condition, molecule starts behaving very differently. Like what cannot happen under the normal regime, I didn't show some of the slides because lack of the time. Helium atom, it is non-reactive, right? But you take it to the extreme pressure condition and bring sodium atom nearby that, immediately it forms helium sodium complex that we cannot even imagine. Helium is very well known that it is an inactive atom, right? But under the extreme pressure, this can be formed. So the pressure can be one of the triggering factor for such observation. Now the question for the water molecules, that even it is the frozen state even at 138 degree, is because enhanced hydrogen bonding. That becomes because of the under high pressure, the phase diagram, if you see it, you don't need to go to the low temperature. The same low temperature effect you can even see at the very high pressure. And that pressure you are not giving externally, but that is provided by the carbon nanotube. And that is why the hydrogen bond becomes very strong between the water molecule, and that doesn't leave the another water molecule, means the interaction, it doesn't become loosened. That is why it exists as the ice molecule. Now, how much force is there and how we can quantitatively estimate that, it is yet to be explored. Am I clear? for your question. Yes. Yeah, thank you. Yes. 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 Well, it's an extremely important and valid, very valid question. This is one of my baby, which has come out from my laboratory just 6 months back. And we use the confinement for different type of thing, but the question of nitrogen reduction and forming the ammonia, this has been going on at the discussion level for uh, last few years. We proposed different type of catalysts, but we could not come out any type of suitable catalyst for nitrogen reduction. Then suddenly one day we thought that, okay, how this confinement can play a role? And that is how a kind of conceptual level we started, and now we could achieve this. The next level is that, of course, we need to take it to the laboratory level, not even industrial level, laboratory level, and then one can think of going to the industrial level. First, we need to establish this concept even at the laboratory level. This is just a theoretical proposal, and we haven't even published. And we have communicated to the journal, but there are many critical questions are there which are yet to be answered. Okay, so this will take probably next few years to come into the laboratory level. Yes, any other question?
Thank you, sir.
Yeah,
So in the interest of time, we'll stop here.
yes, sure. Yeah, thank you
We can
very
take
much.
more questions offline.
doctoral work, Professor Krishnan worked as a postdoctoral researcher at the University of Pennsylvania, USA from 2006 to 2010. Sir then furthered his research career as a research associate at the National Institute for Material Science, Tsukuba, Japan from 2010 to 2012. In April 2012, he joined the Indian Institute of Technology, Mandi, as a faculty member and is currently a full-time professor. Professor Krishnan's research group primarily focuses on green chemistry and heterogeneous catalysis, particularly for energy and environmental applications. Over the years, he has mentored 12 PhD students, 26 MSc students, and he is currently supervising 8 PhD and 7 MSc students, in addition to several short-term research interns. Sir has published over 180 articles in prestigious international journals and serves as a reviewer for several scientific publications. His exceptional work has earned him numerous recognitions, including the DST Inspire Faculty Award, IIT Mandi Foundation Day Award for Excellence in Teaching, MANA Research Fellowship, DOE Postdoctoral Fellowship, DFG Doctoral Fellowship, and DAAT Visiting Scholar Fellowship. In addition of his research and teaching contributions, Professor Krishnan has held several important administrative positions at the IIT Mandi. These include serving as the first warden of the main hostel in the permanent campus, founding coordinator of the Advanced Material Research Center, Associate Dean of Research, and most recently as Dean of Sponsored Research, Industrial Consultancy, and International Relations. He is also the director of IIT Mandi iHub and HCI Foundation, a technology innovation hub, and IIT Mandi Catalyst, a technology business incubator. Outside of his academic work, Professor Krishnan has a keen interest in linguistics and enjoys reading books. We are privileged to have him here with us today. Let's give a warm welcome to Professor Venkata Krishnan.
Sairam everyone. Yeah, good morning. First and foremost, I would like to thank all the organizers, especially Professor Rajni Bandari ma'am, for the kind invitation to attend this conference here. And this is my first visit to Prasanthi Nilayam and Puttaparthi. Although I have been thinking about visiting this place for a very long time since my school days, where I was involved with this SSSIHL Balavikas, but somehow I didn't get an opportunity till date. And when I got this suddenly an invitation, I felt very happy that perhaps Bhagwan has thought about me and called me to this place. So it's really a pleasure to meet and interact with you all. Thank you. So today I'll be giving a talk about some of the research activities of my group. You can listen to it, and then if there are any questions, we'll be happy to discuss, especially with the students. I'll be more than happy to discuss during lunchtime or any other time. Whenever you'd like to approach me, please feel free to approach me. So today I'll be talking about the development of efficient heterogeneous catalysts for different reactions, which includes the transfer hydrogenation, carbon dioxide conversion, biomass valorization, and finally plastic upcycling reactions. Oh, oh, okay. I had to point it out. Yes, since I was already introduced by one of the students, so I'm not going into the detailed introduction. So for those of you who might be thinking where IIT Mandi is located, it's a relatively a new institution. So in order to introduce our institute is located in the state of Himachal Pradesh. It's almost at the center of Himachal Pradesh. It's a place called Mandi. People think about Mandi as like Sabzi Mandi or a market. But although Mandi is, there are markets in IIT Mandi, but interestingly, the name of the place is also Mandi here. And this is where our campus is located, and our campus is located in a place called Kamand. And there is a historical thing that says that the Rishi Parashar, who is the father of Vedvyas, so when there is a Parashar lake over there nearby. I haven't put the photos here. So there when he was traveling to that Parashar hill, so he forgot his Kamandalam over there in this place. So that's how this place got this name Command. This is a mythological thing, but it's a very beautiful and a serene location, and it's nestled in the laps of the Himalayan mountains. So these are the two campuses. This is called the South Campus, this is the North Campus, and our labs are located here in the South Campus. These are some of the buildings of IIT Mandi, and this is where one of our lab is located. It's really a very, very beautiful place, and I would like to invite you all anytime. If, please feel free to visit our place. If you are interested in visiting, please let me know. I'll be happy to make all the necessary arrangements for your visit. Okay, yeah. So first and foremost, I would like to thank all the members of my research group, because they are the main people working behind the scenes, or now I want to bring them at the forefront and thank them in the beginning itself, because many a times I may run out of the time, but here I have been given 40 minutes time, so I can speak a little relaxedly, but I should not be standing in front of you and the lunch. So first and foremost, I would like to thank all the members of my research group who have contributed to this work. And today's talk, I'll be talking about the research activities of 4 of my scholars. 2 of them have graduated and 2 of them are still working with me. So I'll be talking about the works of Dr. Trapti Chabra, Mr. Devendra Sharma, Dr. Hussein Chand, who is now a Marie Curie fellow in Italy, and Dr. Trapti Chabra, she is now working with Professor Beth Sells in University of Leuven as a postdoc. And Ms. Kamlesh Kumari. Kamlesh and Devendra are still working as a PhD scholars in my group. Devendra is a PMRF Prime Minister's Research Fellow, and Kamlesh is funded by the Ministry of Education. So the main focus of our research group is heterogeneous catalysis towards energy and environment, which is well aligned with the term sustainability and sustainable future. And within a part of our research group, we work on several topics. So which includes biomass conversion, how we can make utilization of a large amount of waste biomass, which is how we can convert that biomass into something which is really useful, such as the fuels. So how to do it catalytically. And another area is the organic transformation, wherein we mainly focus on green and sustainable chemistry. We take all very well-known reactions, especially the industrially relevant reaction, and try to see how those reactions, which are being done in the industry in a more non-sustainable way, and how to bring it little more sustainable. For example, how to design a catalyst which is earth abundant and it's more sustainable, how to reduce the usage of toxic chemicals and solvents, and how to do it in a more efficient way, less time consuming way. And the third area which we are working on is the carbon dioxide reduction or the carbon dioxide conversion. Here again, the concept which Sir was mentioning, the previous speaker, Dr. Chandrakumar was mentioning about the curvature. So this carbon dioxide molecule, which is a linear molecule, if it can be bent, and how the bending of the carbon dioxide molecule makes it much more reactive, and it can be fitted within the epoxide type of a structure in order to make cyclic carbonate. I'll be talking about it little more in detail in the subsequent slides. And another area, these 3 areas, the biomass conversion, organic transformation, and the carbon dioxide conversion, these 3 we work in thermocatalytic domain. And another 3 areas which we work on is the hydrogen evolution, which is again related to energy, which is the water splitting. So how this water molecule, the H2O, can be split into H2 and O2, and the evolved H2 can be used as an energy source. So that was also spoken by Dr. Chandrakumar, that the hydrogen is one of the beautiful energy source which has the highest energy density. So how we can obtain that hydrogen? And water, it's again another abundant resource which can be used to obtain the hydrogen. And next, we are also working on nitrogen fixation. Again, the previous speaker spoke about, which is the ammonia production. So our nitrogen, about 78% of the air contains nitrogen. or nitrogen is the 78% in the air, and hydrogen can be obtained from water, which is again a renewable resource, and we can use the sunlight, which is also a perennial and a renewable resource. Can we combine all the three natural available and renewable resources and make ammonia, which is one of the most important molecule. So with the help of our catalyst. So that's one thing, but in the interest of time, I'll not be talking about a nitrogen fixation today, but if any of you are interested, we can connect offline and I'll be happy to discuss some of our works. Again, it involves the same thing like this triple bonded nitrogen, how we can kind of fix it and convert not only into ammonia, but we can also convert into nitrates and nitrites, which is also involves the nitrogen fixation, which will also be very helpful in this regard. And finally, we are also working in the domain of pollutant degradation because we want a clean environment. So for that, we need to remove the pollutants, and these pollutants come from various sources like the pharmaceutical industry, the dye industries, and many such industries. So these pollutants can be broken down into much smaller and non-toxic fragments by the help of photocatalyst, and these can be kind of pollutants which are broken down can also have certain other uses as well. The smaller molecules which can other uses as well. So this is the overall goal of our research work, and beyond this we have recently started working on plastic upcycling as well. Yeah. There's a need for sustainable development. So since the conference is also organized in sustainable development, we keep talking about sustainable development. Why there is a strong dire need for the sustainable development and how we can bring in those sustainable development. So when we look at the conventional approaches like the Haber-Bosch approach, which Sir was mentioning about, and also the complicated organic synthetic approach, which Professor Brahmachari was mentioning about, this use expensive metal-based catalyst, high temperature, high pressure, harmful solvents, toxic reagents, and also the process is entirely very difficult to manage. On the other hand, when we look at the sustainable approach, it uses metal-free or inexpensive catalysts. Pretty much we would like to use non-toxic metals and the metals which are available in plenty. And if at all we have to use any other rare metals, use in a very minimal quantity without affecting the environment. And pretty much we would like to focus on metal-free catalyst. How without a metal, the catalytic reactions can happen. And then using mild reaction conditions of low temperature and using atmospheric pressure without having an additional pressure. Now I understood from the previous talk that we can create some confined spaces to kind of artificially induce pressure. But here in this type of cases, we even use normal atmospheric pressure to try to do the reaction. It may take a longer time, but nevertheless, in the interest of the energy saving, this could be one of the better approach. Then use of environmentally benign solvents, and finally we could have reduced waste and less detrimental impact on the atmosphere. Next slide, please. Yeah. So now how to bring in this sustainable development. So since our group is working on heterogeneous catalysis, we could kind of think from a catalysis point of view. There could be many other ways, but different researchers and different groups are working on several different strategies. But since our group is working on the catalysis strategy, we are thinking about more in terms of the catalyst. So we could kind of artificially induce certain catalyst design constraints. So we kind of have a self-imposed constraints in order to design the catalyst, like use of earth-abundant elements, predominantly metal-free and low-cost materials to develop the catalyst. Use of non-toxic and non-polluting chemicals and processes for the entire catalytic reaction, so we can bring in sustainability. Use of relatively low temperature, that is less than 250 degrees C for the catalytic reaction. This is also something which is very important because the energy saving is there, and there would be less carbon emission. Like morning your Vice Chancellor was talking about decarbonization. So how to kind of reduce this carbon footprint. Then use of ambient pressure for the catalytic reactions, and finally adherence to all the 12 green chemistry principles to the best extent feasible. Morning Dr. Brahmachari was talking about the green chemistry principles, how we can best adhere to the green chemistry principles, and finally catering to all the 17 UN sustainable development goals, and within our group we are trying to cater to 5 of those 17 sustainable development goals. So next slide. So these are the 12 green chemistry principles. Since we already heard a detailed lecture about the use and applications of the green chemistry, I'm not going to touch upon this, but this is from the textbook. If any of you are interested, you can have a look at the green chemistry principles. And these are the 17 development UN Sustainable Development Goals. Your Vice Chancellor was mentioning that chemistry is really the underlying concept of all the 17 UN Sustainable Development Goals. You can think from any angle. So obviously there would be some or the other chemistry would be involved in all the 17 Sustainable Development Goals. And within these goals, we would like to focus on clean water sanitation, affordable and clean energy, responsible consumption and production, climate action, and partnership for the goals. These are the 5 aspects we would like to mainly focus on. Thanks. So how we are trying to do that? There was also a question that why carbon materials are unique. Obviously, I'll also be talking about carbon materials, but not just a simple carbon, but carbon nitrogen type of materials, which is the graphitic carbon nitride and also other forms of carbon nitride materials. As you can see, this carbon nitride material is composed of carbon and nitrogen atoms, both of which are earth abundant and easily available. And interestingly, both of them are gaseous, especially the nitrogen is gaseous, but when we can combine it with this carbon, we can get this unique type of a structure, which is the carbon nitride material, which can be used as a catalyst for various applications. And these carbon nitride materials can be synthesized very easily by several different strategies, like using polymerization of cyanamide or dicyandiamide, melamine, or urea. There are several different chemicals which can be used for the preparing this graphitic carbon nitride material. And these materials are very stable chemically as well as thermally. So if you kind of put it in some acid or a base, these are quite stable, and also it is stable to about 400 degrees centigrade or about 450 degrees centigrade, which is much higher compared to the reactions which we are doing, because we don't want to go beyond 250 for our reactions. And these materials are also amenable for surface functionalization. You can even play with these materials by kind of introducing different surface functional groups like the sulfonic acid group or the phosphate group or nitrate group, or you can even have the doping, like you can instead remove one of the carbon atoms or the nitrogen atoms and put a boron atom in order to induce the Lewis acidic nature to this material. So you can play with this material with multiple ways in order to introduce your desired properties onto this material. This is how this graphitic form of carbon nitride material looks like. Next slide, please. Now, moving on to the first part of the talk, which is on biomass valorization. As we keep talking, there is a huge amount of biomass, which is the waste material. When we look at it, this biomass is also composed of carbon, nitrogen, oxygen, and different, mainly these elements, and also the nitrogen. And when we look at the fuels or other useful molecules, the elements are almost the same or exactly identical elements are there, but the structures are different. So how we can kind of tune these structures in order to convert the waste biomass into something which is very useful. Either we can make a pharmaceutically useful molecule, or we can make a biofuel type of material, or something which is composed of the same elements, but the structural arrangement is different. How can we bring in this type of thing? So we took one of the materials, or one of these biomass derived materials, which is the saccharides. Saccharides are very common, and most of you are familiar with this. And we would like to convert these saccharides into a platform chemical. A platform chemical is something like it's a chemical. From there you can make different chemicals, like pharmaceutical or a nutraceutical or even a jet fuel or different type of chemicals. For example, if you'd like to go from Puttaparthi to Delhi, you first go to Bangalore and then take a flight to Delhi. If you want to go to Chennai, again you could go to Bangalore and then you can take a flight to Chennai. So the Bangalore is like a platform chemical, where if you reach there, you have the possibility to travel to different places. So similarly, a platform chemical is somewhere you go and then you form, and then you get that chemical converted into something which is more useful. So we took this saccharides and converted it selectively to this other useful chemical, which is the platform chemical, which is the 5-hydroxymethyl furfural. In short, it's called 5-HMF, and we did it in green solvents. This work was done by my former PhD scholar, Dr. Tripti Chabra. and we prepared this catalyst, which is the sulfonated graphitic carbon nitride. This sulfonated graphitic carbon nitride, this catalyst has both Bronsted base as well as the Bronsted acidic sites. The Bronsted acidic sites come from the sulfonyl functionalization onto this graphitic carbon nitride, and the Bronsted basic sites comes from the intricate nitrogen atoms which are already found in this graphitic carbon nitride. Then we converted this saccharides. We took different saccharides, the monosaccharides, which are the glucose and fructose, and also the higher saccharides like cellulose, sucrose, and starch, and we converted it into a highly selective chemical, which is the 5-HMF. And we converted it using different green solvents. So it can go with water, ethanol, isopropyl alcohol, and also dimethyl carbonate. So several chemicals are the green solvents can be used for this conversion process. And finally, the synthesized 5-HMF can be converted into other value-added products. For example, 2,5-bis hydroxyl methyl furan, 5-chloromethyl furfural, and also 5-bromomethyl furfural, because it's a platform chemical. So once you reach Bangalore, your final destination is somewhere else. Someone wants to go to Chennai, someone wants to go to Calcutta, someone wants to go to Delhi. So there are different things. So we kind of proved that it can be converted into other useful chemicals. Next slide. So first and foremost, when you develop a catalyst, design a catalyst, and prepare a catalyst, first we need to know whether our synthesis is successful or not. And secondly, we need to know what type of structure is formed in the catalyst, and also what is the morphology of the catalyst. In order to understand this, we need to do different characterizations of this catalyst. So first we did the X-ray diffraction, the XRD characterization on the catalyst for both the simple graphitic carbon nitride and also the sulfonated graphitic carbon nitride material. So from that we were able to understand that this material is successfully formed. At least the structure matches with the literature reported structure. And we have this functional groups, the SO3H functional groups. To understand the functional groups, we did the Raman spectroscopy and also the FTIR spectroscopy. These two indicates that the functional groups are present on this structure. Then we did the thermogravimetric analysis for both the graphitic carbon nitride and also the sulfonated form of graphitic carbon nitride. And the graphitic carbon nitride is much more stable to about 450 degrees C. And this material is also stable to about 350 to 400 degrees C, which is much higher than the temperature where the chemical reactions took place. Next slide, please. And then we did the morphological studies using SEM. SEM stands for the scanning electron microscopy, and TEM. TEM stands for the transmission electron microscopic techniques. So we did these two techniques in order to understand what type of morphology. Morphology means what type of shape this catalyst is having. So from this analysis, we were able to find that it exhibits a sheet type of a morphology. This both the graphitic carbon nitride as well as the sulfonated form of the graphitic carbon nitride. We also did the EDAX analysis and also the EDS mapping in order to understand which elements are located in the sample. Next slide, please. We also did a detailed XPS analysis, which is the X-ray photoelectron spectroscopy. And from this technique, we were able to get what is the oxidation state of each of the elements present in the material, and what is the interaction of each element with the other element, like how carbon interacts with the nitrogen, how nitrogen interacts with the sulfonic group which is connected in the material. So these interactions we can get to understand from the XPS spectroscopy. And also this XPS is a surface sensitive technique. So from this technique we are also able to get how much of a sulfur atom is present on the surface, which is about 3.27 atomic percentage. And then we used this material as the catalyst for this reaction. From starch we get this glucose and fructose, which gets which forms the 5-HMF selectively using our catalyst. Next slide, please. Then we did a detailed optimization of the different parameters. First we optimized the catalyst amount. We are using different amounts of the catalyst ranging from 5 milligrams to 30 milligrams, and found 10 milligrams to be the optimal catalyst amount for this reaction. Then we optimized the temperature and found 200 degrees centigrade is the optimal temperature for this reaction. Then we also optimized the time. We tried for different time periods ranging from 3 hours to 7 hours and found 5 hours as the optimal time for this reaction. Then we examined the different saccharides ranging from the monosaccharides, which include the glucose and fructose, and also the other saccharides which include cellulose, sucrose, and starch. We also tried the reaction with different green solvents, so ranging from water, ethanol, IPA. IPA is the isopropyl alcohol, and DMC, dimethyl carbonate, both for the monosaccharides and also for the higher saccharides. And for interestingly, we found that for the glucose, we got the highest yield of formation of the 5-HMF. We also studied the recyclability of our catalyst because our catalyst is heterogeneous in nature. So ideally, the catalyst should be recovered and reused multiple times. But over the period of time, there is a decrease in the activity of the catalyst, which indicates that there is something going on with the catalyst. And we were able to figure out that during the process of this conversion, wherein 5-HMF is being produced, there is also this humins which are being produced, which are polymeric carbonaceous material. And these humins are getting stuck on our catalyst material and blocks the catalytic active sites. And that is the reason for the decrease in the activity of the catalyst. So we were able to figure it out why there is a decrease in the activity, but we are able to get an understanding of the structural stability of the catalyst as well. Next slide. Oh, sorry. We did the evaluation for the different green matrix parameters, as Professor Gautam Brahmachari pointed out about the importance of the green matrix parameters. Whenever we call a reaction green, we need to know how green it is. Okay, I passed this course. So, okay, how much marks did you get and pass the course? What was your grade? So, similarly, if you call any reaction green, it's better to kind of make some metrics and understand the greenness of the reaction. So, we evaluated the different green matrix parameters since it was already introduced. So, I am not introducing the green matrix parameters, but we kind of evaluated for the different reactants and found that they all have a very good values for the green matrix parameters. Next slide, please. Then, as I mentioned, this formed 5-HMF, which is a platform chemical, was converted into other useful chemicals like 2,5-bis hydroxy methylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural using normal processes, and got decent yields for them, which indicates that this is really acting as a platform chemical. Next slide. And this work was published in the journal Green Chemistry with my student Tripti Chabra as the first author. Next. Subsequent to this work, we thought that okay, the presence of the acidic and the basic groups on the same catalyst is enhancing the catalytic activity. We have the sulfonic acid group as well as the nitrogen group in the graphitic carbon nitrate, which is giving the basic property. Okay, what will happen if we introduce an additional acidic site onto the catalyst? For example, if we dope the catalyst with boron. So we will have both Lewis acidity coming from the boron doping and also the Bronsted acidity which is coming from the sulfonic acid group. So if we have this dual type of acidic nature as well as the Bronsted basic nature from the graphitic carbon nitrate, will the activity overall increase? So we thought we were greedy and then we tried this, but unfortunately it didn't work out that way. Only the Lewis acidity it giving a better result, or only the Bronsted acidity is giving the better result, but a combination of Lewis and Bronsted acidity did not give the good result. We were expecting that they will work synergistically, but unfortunately they were working non-synergistically. But nevertheless, this gives a lot of learning that why certain things doesn't work. And nevertheless, we kind of made this work in a much more detail, and we were successful in publishing this work in this journal Carbon in 2021. Next slide. And we also worked on another material which is also a sustainable material, which is a hydrochar. And we derived this hydrochar from a waste biomass, which is the waste orange peel. And then this hydrochar material could be functionalized with the sulfonic acid group, phosphate group, and the nitrate group one at a time. And then we used it for the solventless synthesis of biofuel precursors. And this work was also published in the Green Chemistry journal. Next slide. And this work also got a lot of media attention during the time of its publication in 2022. And we also introduced another material as a catalyst for the same type of a reaction, which is again the solventless synthesis of biomass derivatives to high carbon biofuel precursors. Here we kind of took an inorganic material, inorganic oxide. And again, we functionalized this inorganic oxide with sulfonic acid group, the niobium pentoxide with sulfonic acid group, and used it as a catalyst for this reaction. And this work was published in Fuel in 2023. And recently we have written a detailed review article for this Chem journal, which got published in 2024. It's yet to get its actual page numbers, but it's available online, wherein we kind of described how this layered double hydroxide, which is also another very beautiful and interesting material, easy to synthesize material, how this can be used for different biomass conversion reactions, wherein we could valorize the waste in order to create wealth. Next. So now moving on to the second part of my talk, which is on organic transformation. So in this organic transformation, mainly we took this reaction, like which is the transfer hydrogenation reaction, catalytic transfer hydrogenation reaction. This is a very interesting and important reaction because we do not need to use this molecular hydrogen, because handling molecular hydrogen is very difficult. Because the hydrogen, it's a flammable gas, so if there are any accidents, it would be a catastrophe. So we do not want to use this molecular hydrogen, which is being used in the industry. But instead of molecular hydrogen, where can we get the hydrogen? So we could get this hydrogen from a biorenewable source during the process. So as the hydrogen gets it's a transfer hydrogenation reaction. The hydrogen gets cleaved from one molecule and it gets attached to another molecule and the reaction proceeds. So this is the reaction which we took as the model reaction, which is the quinoline to 1,2,3,4 tetrahydroquinoline. So this is the transfer hydrogenation reaction. We are able to achieve this reaction using a catalyst which is the nickel phosphide with graphitic carbonitrate. So it's the synergistic coupling between the nickel phosphide and the graphitic carbonitrate kind of leads this reaction. There is a synergistic coupling, and this reaction was carried out without any base. Again, it's a environmentally friendly reaction and without any molecular hydrogen. And it's a simple transfer hydrogenation, and the hydrogen comes from a biorenewable source. It comes from the formic acid. And then we could investigate the ligand and also the ensemble effects, how they influence the reaction. Similar to the previous cases, we use very simple strategies to prepare our materials, and these strategies are quite well reported in the literature. First, we prepare the graphitic carbonitrate, then we prepare the nickel phosphide nanoparticles. Basically, although we call it as nickel phosphide, indeed this is a alloy type of a material, because the nickel exhibits a zero oxidation state predominantly, and phosphorus also exhibits a zero oxidation state. We call it as a delta plus and delta minus just for the namesake, but it's an alloy type of a material, the nickel phosphide. It's also relatively easy to synthesize. Then we prepare this composite in varying proportions. Then, similar to the previous cases, first we need to understand whether our material preparation is successful and what is the morphology of the material. For that, we did the detailed characterizations, which is the X-ray diffraction, the FTIR spectroscopy, the thermogravimetric analysis, and also the stability test of the material in various different harsh conditions. Although we did not use any harsh condition, but we just wanted to check the stability. Next slide. Then we studied the morphology of the material. The nickel phosphide material exhibits a nanoparticle type of a morphology, whereas the graphitic carbonitrate is a sheet type of a morphology. For example, you can imagine there is a big carpet and there are certain balls which are floating on the carpet. So this is the kind of imagination of the morphology of the material. Then we did this EDAX mapping in order to understand where which elements are being located and spatially distributed. We did a detailed analysis of this morphological morphology of the material. Next slide. We also studied the material in detail using XPS technique in order to understand the oxidation state, the nature of interaction of the different elements with each other, and also what is the surface composition of this material. And from the XPS analysis, we were able to clearly decipher that the nickel exhibits predominantly the zero oxidation state and also a little bit of the +2 oxidation state, because the material which is on the surface will exhibit some sort of an oxidation. So that's why we call it this as the delta plus. And similarly, we have the phosphorus in delta minus or oxidation state. And then we tried this reaction wherein the quinoline gets converted into tetrahydroquinoline in the presence of the catalyst solvent and a temperature under time. And here we are using this formic acid, which is a bio-derived hydrogen source. So we can take the formic acid from a bio-derived source, which is renewable in nature. Then we did a detailed optimization wherein we optimized the temperature, time, catalyst amount, solvent, hydrogen source and also the catalyst, the individual components of the catalyst. We could use a different type of hydrogen source, but with the formic acid, it gave the highest catalytic yield. And interestingly, this reaction can go well with the nickel phosphide as well as the graphitic carbon nitride, but the combination gave the higher yield. And in the combination, there is only 10 weight percent of the nickel phosphide, and rest of the thing is the graphitic carbon nitride. So the amount of metal which is used is very less. And also nickel is a non-noble metal, and it's also quite well abundant metal. Then we did this reaction with different substrates. We examined the substrate scopes, and these are the different substrates. We are having different functionalities, like one having a electron withdrawing group, other having an electron donating group, and then we were able to prove the generality of this reaction. Next slide. We also did a detailed computational analysis of the system in order to understand how the catalyst performs this reaction, and this computational work was done in collaboration with my good friend Dr. Saswata Bhattacharya from IIT Delhi. Next. We did also the mechanistic understanding of the reaction, again using computational tools, the DFT based computational tools, in collaboration with the same Saswata Bhattacharya. Next slide. So this work kind of elucidates the synergistic effect and the reaction mechanism of how this nickel phosphide combined with the graphitic carbon nitride can be used as an efficient catalyst for this transfer hydrogenation reaction. This manuscript is currently under review. Apart from this, we have again used the same type of a material, which is the nickel phosphide, which is supported on a different type of a material, which is the activated carbon material, and this was also used for transfer hydrogenation reactions, because this nickel is a very good for this transfer hydrogenation reaction. We examined this transfer hydrogenation for this nitroarenes, and we were able to demonstrate that it can happen under mild reaction conditions, and this work was published in the Journal of Colloids and Interface Science in the beginning of this year, 2024. We also wrote a detailed review article for this journal SMALL, which is a biology journal, on the beauty of this transition metal phosphides, how this transition metal phosphides can be explored as a catalyst for doing various organic transformation reactions and in the field of organic catalysis. Then we have written another review article on the catalytic transfer hydrogenation reactions using non-noble metal based heterogeneous catalyst, because this is one of the most important reactions which is valuable for the industry. There are several, this is one of them. And in this case, many of the industries are using noble metal based catalyst under pressurized conditions, but we had kind of selectively picked up how the non-noble metal based materials can also be used for this reaction, and this is a review article written for ACS catalysis. It got published in this year in 2024. All this work were done by my student Devendra Sharma, who is currently working with me. Now moving on to the third part of my talk, which is on carbon dioxide conversion. Here we prepared a novel forms of carbon nitride. In the previous slides you might have seen I have used this carbon nitride material, especially the graphitic form of carbon nitride material, which was prepared using a high temperature process. We have used 500 degrees centigrade for the preparation of the material. Although the catalytic reactions were done at a much lower temperature, but the catalyst preparation took a higher temperature. Whereas we wanted to optimize the catalyst also to be prepared at a low temperature. So we prepared two different forms of carbon nitride. We don't call it as a graphitic carbon nitride because the structure is not that of a graphitic material, but we prepared the two other forms of simple carbon nitride material, one using the 5-amino tetrasol and another using 3,5-diamino triazole. One is tetrasol, which is named as 4NZ, another is triazole, which is named as 3NZ, and CN stands for the carbon nitride. And in both the cases, the cyanuric acid was the starting material. So we prepared these two materials as the catalyst, and we used it for this carbon dioxide conversion, wherein we converted the epoxide into cyclic carbonate. So where the carbon dioxide molecule, which is a linear molecule, gets bent and gets inserted into this epoxide ring in order to make the cyclic carbonate ring. And this is how the materials have been prepared. It's a very simple process of how to prepare the material. And as you can see, these materials have been prepared in just 100 degrees centigrade under reflux conditions in a very short period of time of 2 hours. Just the drying time and the stirring time, and we were able to get these materials, and we were able to get it reproducibly, even if the temperature is relatively low. And similar to the previous cases, if we prepare a material, we need to understand its structure and also the morphology. So we studied this material using X-ray diffraction, FTIR spectroscopy, the Raman spectroscopy, and also the stability of this material under the thermogravimetric analysis. So we were able to get the see that the material is quite stable, but not as stable as the graphitic form of carbon nitrate. But this material is also quite stable to come slightly about 200 or 250 degrees centigrade. And we study the morphology of the material, although the process which are used for the preparation of the triazole and the tetrasole component of the graphitic carbon nitrate are almost identical, but nevertheless the morphologies were very different. In one case it forms a particle type of a morphology, in the other case it forms a tubular type of a morphology, which is very interesting. We don't have a control of the morphology, we could only see that, oh, this is the morphology which is being formed. We did the XPS analysis in order to understand the interactions between the different components much better. Next, we did a detailed optimization of this catalytic process using different set of parameters. So the main reaction is the carbon dioxide getting inserted onto the epoxide ring in order to form the cyclic carbonate. So we optimized first the catalyst amount, then the temperature, then the time, and also we used a different type of co-catalyst which are also cheap and easily available, like the potassium iodide type of a co-catalyst we have used, and we got the good conversion in both the cases. While if we see this triazole performed better than the tetrasole moieties here. Then we also studied the substrate scope, wherein we used different type of epoxides which have different substituents, and including an epoxide which is a linear type of an epoxide, which is also has some other epoxides which has some cyclic functionality. There is something more to it, and we kind of studied how this material performs, our catalyst performs, and we were able to kind of figure out what is the yield and also what is the turnover number in each of these cases. We also studied the recyclability. While the tetrasole is not as good recyclable, but the triazole moiety, triazole containing catalyst was quite good reproducible, and it also showed structural stability as well. And this is to kind of conclude. So the catalyst, both the catalysts show excellent yield, but one of the catalyst has a better recyclability compared to the other catalyst. And this work was also published in this Journal of Colloids and Interfaces in this year, in 2024, with my former PhD scholar, Dr. Hussein Chand, as the first author. We also patented this work, and the patent has been just recently granted in the month of November. We also published another work wherein this graphitic carbon nitrate is a very interesting material, and as I said in the beginning, there are different type of sources which can be used for the preparation of the graphitic carbon nitrate. But the formed material, the graphitic carbon nitrate, although the things are quite similar, but the activity of the graphitic carbon nitrate prepared from various sources are different in comparison to the other forms of graphitic carbon nitrate. So we undertook a study wherein we prepared the graphitic carbon nitrate using different sources and made a detailed comparison of the formed graphitic carbon nitrates for this particular reaction, which is the carbon dioxide conversion. And that work was published in this journal Fuel in the beginning of this year, where it is a very detailed comparative study. It's a known reaction, a known catalyst, but how the preparation procedure of the material influences the final activity of the catalyst. And now moving on to the final part of my talk, which is on plastic upcycling. So I understood that this conference is sustainable and they are giving water in a steel glass and not in plastic bottles, which is really very good. But in case if there are any plastic bottles, we could see a lot of plastic bottles in and around, not perhaps in your campus, but in our campus we could see a lot of plastic bottles. So what can we do with these waste plastic bottles, the PET bottles? Can we convert the PET into something which is useful? So there are a lot of different strategies, not lot, there are a couple of strategies which can convert this PET into other useful chemicals. So one of the strategy is this methanolysis. and we prepared a catalyst for doing this methanolysis. So we could do the methanolysis of the waste PET bottles, and the uniqueness about our work is we used a non-noble metal based catalyst for this conversion. So we used a cobalt based material as a catalyst for this conversion, which has a high surface area and stability, and it could do the catalytic reaction under mild reaction conditions, and we could get an increased conversion in yield. So PET got converted into DMT. This work was done by my current PhD scholar Kamlesh Kumari. And this is how the catalyst preparation works. The catalyst preparation is relatively simple. So just by kind of doing some simple stirring in the presence of a reducing agent, we were able to get cobalt nanoparticles, and we took commercial silica. Commercial silica is very cheap. We took this commercial silica and then integrated our cobalt nanoparticles, and then we got this cobalt nanoparticles decorated on the silica matrix. And this we used it as the catalyst for this conversion reaction. Next slide. And similarly, we did a detailed characterization of the catalyst using various techniques, including XRD, FTIR, and also the SEM and the TEM in order to understand the morphology of the material. And we also did the XPS analysis to study what is the oxidation state of cobalt and how the cobalt interacts with the SiO2 which is present in the material. And this is the reaction. So this plastic bottles, we took the real plastic bottles, cut them into small pieces. We could have also used a ball mill, but since we didn't have the ball mill, but we just cut it with some scissors in order to make it as small particles. Then this PET interacts with this methanol because it's a methanolysis in the presence of our catalyst at a certain temperature to give this important product, which is the dimethyl terephthalate. The dimethyl terephthalate has many uses, and this could be further converted into many other products as well. This is for the methanolysis. We could convert it, PET into BHET through another process, and through aminolysis we could also convert it into some other product. So there are many strategies which are available, but we did the methanolysis, and this is how the process worked, and finally we were able to get the DMT. And we did a detailed optimization. We optimized the cobalt loading on SiO2, and with a very minimal loading of 5%, we were able to still get the conversion. And if we increase the loading to about 10, we were able to get the maximum conversion, which is conversion and yield, which is possible. We also optimized the catalyst amount, we optimized the temperature, and also we optimized the timing of the reaction. Even with 2 hours, we were able to see some formation of the DMT, but when we increase the time, optimize the time, with 6 hours we are able to get the very good yield. And this process not only works with the simple colorless PET bottles, but we could take even the other colored bottles like the Mountain Dew bottle, the Sprite bottle, and also the mixture of different colored PET. It works equally good for pretty much all the different PET. We could get a PET conversion 100%, while the DMT yield varies slightly, but it's still within the error bar limit. And this is the process, and we also demonstrated the scale up to about 5 gram scale, because that's what is feasible from our laboratory. We increased the scale in order to demonstrate that this reaction has a potential to be scaled up. We also studied the recyclability of the catalyst by doing the reaction with the same catalyst multiple times, and we checked the stability and the structural integrity of the catalyst by doing the X-ray diffraction analysis of the fresh catalyst and also the spent catalyst after the 5 reaction cycles. Next slide. Next slide, please. Yeah, we examined the mechanism of the reaction as well. In the interest of time, I'm not going into the mechanism. Next slide. And this work was published again in this year, in the middle of this year, in the journal Catalysis Science and Technology. Oops. Previous slide. We have written a very detailed review on there are various strategies to upcycle the plastics. Although we consider plastic as a waste, but why don't we consider plastic as a resource? And it's a sustainable, not directly a sustainable resource, but a resource which could bring in sustainability if we could kind of close this loop of the circular economy. So we have kind of summarized in this review the photocatalytic, electrocatalytic and photoelectrocatalytic strategies for plastic upcycling and how way towards circular economy, how we can bring in the circular economy. And this work was also published in the same SES Catalysis journal in this year in 2024. And finally, to conclude, our group is actively working in the domain of heterogeneous catalysis for energy and environment. And in the brief time of, or in the long time of 40 minutes given to me, I don't know how much I exceeded the time, we were able to kind of tell you some of our work in the field of biomass conversion, the organic transformation, the carbon dioxide reduction, and finally about the plastic upcycling. Next slide. A piece of advertisement. So currently I serve as the associate editor for this new journal of chemistry. So if you have any good works which you would like to get published in this journal, you are welcome to please submit your works to this new journal of chemistry, which is published by RSC. It's free to free to publish and free to not free to read, free to publish. If your institute has subscription, you can read this journal. And I also come serve in the editorial advisory board of this ACS journal called ACS ESNT, Environment Science and Technology Engineering. So if there are any other environment science and technology related works, you may please submit to this journal as well, which is also free to publish and subscription to read. And finally, I would like to once again acknowledge all the members of my research group, faculty colleagues and staffs at IIT Mandi, and research collaborators both within and outside of IIT Mandi, and finally the Advanced Material Research Center for all the instrumentation facilities. All the techniques which I showed here are used from our institute, the Advanced Material Research Center, and these facilities are open to all, obviously on a chargeable basis. Even as internal users, we also pay some charges. If any of you are interested to use any of these facilities, for example, like XPS, TEM, SEM, or NMR, you may please feel free to write to me. I'll connect you with the corresponding office and you can interact with them and then send the samples for the measurements. And finally, the different funding sources. And thank you all. Thank you very much. I'll be happy to answer any questions now. Yes, Aman. Yes, yes.
For your wonderful and detailed presentation. So my question is about the plastic upcycling.
Sure.
So given the increasing amount of plastic pollution in today's society, I personally think that there's a need for large scale plastic upcycling. So is this process scalable, or how is the scalability of this process?
Yeah, it's a very good question. Definitely the process is scalable, but obviously with necessary equipments and all, it could be definitely scaled. In our laboratory, we demonstrated the scalability to up to 5 grams. That is the scalability we could demonstrate in the laboratory. But if there are any industry or anyone interested, we could easily prepare the catalyst. One is the catalyst scalability, and secondly the process scalability. So both can be achieved. From our domain, the catalyst scalability is feasible, and with the necessary equipments, the other process scalability can also be achieved, because this process requires a relatively low temperature and very less time. About 6 hours is the optimized time we could do this reaction, and with the amount of catalyst which is also less, and the catalyst is also regeneratable, so we could bring in. So the entire thing can be scaled up. There is a potential for good scalability. Thank you. Yes, yes, please. Sorry. Sure. Oh, boron nitride, it is possible, but we have also tried it. We have also published 2 papers on boron nitride as well, not for the biofuel, but for other organic transformation reaction. There are a couple of issues with boron nitride. One is boron. Boron is not earth abundant. Boron is very like 0.005% and is the overall availability on the earth. So, and secondly, boron, when it combines with nitrogen, boron is electron deficient, whereas nitrogen is electron rich, and when they make a bond, it's very, very difficult to further functionalize the boron nitride, because boron nitride is a highly thermally stable material, and also it's not easily prone towards functionalization. Whereas carbon nitride, you could functionalize it very easily and throughout, and you can even do doping and further functionalization. With boron nitride, when we tried to do the functionalization, we could get to do only the terminal functionalization, which is very, very less amount of the functionalization. For example, for graphitic carbon nitride, after functionalization, we get about 3 to 4% of the sulfonyl group. Whereas if we functionalize the boron nitride with the same amount, we will get very, very meager amount, less than 1% of the functional group, because it's only very surface or the terminal, not surface, but only terminal functionalization. So because of these difficulties, considering the expensiveness of the boron, non-earth abundantness of the boron, and also its non-amenability towards the surface functionalization, we prefer not to use boron nitride, while other cheaper alternative is carbon nitride material. But definitely boron nitride has a scope for other applications. If you need very, very high thermal stability, boron nitride is the material to go. But very good question. Thank you. Yes.
For the talk.
Can you talk a little bit louder?
Sairam sir.
Yeah, now I can hear you.
Thank you for the talk, sir. The most commonly employed approach to valorize this biomass is traditionally to make a activated carbon out of it, where we heat it at higher temperatures to eliminate the organic moieties.
Yeah.
But in particular, my doubt is, sir, when we are using it for an organic transformation, the purity of the product or the precursor becomes a concern. And
Yeah.
how important it is for us to purify the precursor, whereas in case of a saccharide, how should we purify the saccharide before taking it for the transformation, or how like per se we are using a hydrochar directly for a transformation, and how important it is to purify the products, and how tedious it is to purify the product when we are using this biomass based things.
Exactly. Yeah, that's also a very good and very relevant question. So one is the transformation of biomass into some carbonaceous material. Like in our case, we prepare the hydrochar, and some other cases they prepare the biochar and different carbonaceous material. That is one strategy, but that is not a very value added product. That not that much value added, because you think from the cost point of view, you can get 1 kilo of hydrochar maybe for perhaps for 10 rupees. I'm just giving a random example. But similarly, 1 kilo or 1 liter of say diesel or a petrol, you get it at around 100 rupees. So there is a big difference in the cost. So if we can kind of convert the biomass into more value added product, which will be more advantageous comparing to a lower value added product. This is also not zero value, but this is also has a value, but this value is limited in comparison to the other. So we have done in both the cases. We have prepared the hydrochar, and we also prepared other biofuel precursors. So this answers first part of your question. More value added product is more desirable. And the second part is how to purify the thing. For hydrochar, we are heating at a very high temperature, and it's the hydrochar which will form. So we do not need to worry much about what are the other ingredients, because at that high temperature, pretty much everything is gone. Then we did the functionalization and used it as a catalyst for the conversion reaction. So purification of the hydrochar or the formed biochar is not of that much importance, especially for our work. On the other hand, when you prepare some other compound like saccharides to HMF, the HMF, since it is formed selectively, so if it forms selectively, you do not need to worry much about the purification. Whereas if it is some other thing, if there are 2 or 3 products which are being formed in various amount, one gets formed in 80% yield, another gets formed in 15% yield, and the third product gets formed in 5% yield, something like that, then you have to use the purification, wherein you can use the column chromatography for the purification, or recrystallization could be another technique for the purification, or rotovap could be a process for the purification. There are some established techniques depending on what is the boiling point or the melting point difference between the different compounds and how they could be extracted and purified. There are different strategies, and purification is an additional step, which is an energy we have to input some energy, but depending on which process you are employing, whether it's the recrystallization, lower, relatively lower energy requirement. If it is a column, it's more energy and more effort requirement because someone has to kind of put the material into the column and get it purified. So it depends from thing to thing. The ideal case scenario is how to tune the selectivity so that you get the predominantly one product. If you are getting 100% selectivity for a single product, that's the best way to do it. Then further purification from the impurities is not required. Fine. Thank you. Any other questions? Thank you.
Sairam. We thank Professor Venkat Krishnan for drawing parallels between conventional and sustainable approach of synthetic routes, the constraints involved in catalyst design, applications of carbon nitride materials, biomass valorization and its application in conversion of saccharides to platform chemicals using green solvent, followed by its detailed characterization and optimizations, and importance of quantifying the green metrics parameters. Organic transformation, where illustration of catalytic transfer hydrogenation using bio-derived hydrogen source with results were depicted. Carbon dioxide conversion with novel carbon nitrides and catalyst assisted methanolysis of waste PET bottles were presented with examples. Thank you, sir, for bringing out innovative methods towards sustainable green chemistry approach. We now request our esteemed senior faculty, Professor C.N. Sundareshan, to offer a token of love to Professor Venkat Krishnan. Sairam. We thank all the three distinguished speakers of this morning session for their scintillating talks and the audience for their active presence and participation. We'll now break for 1 hour lunch and resume the afternoon session at 1:40 p.m. During the afternoon session, we'll have two technical talks followed by a faculty presentation of the Department of Chemistry, SSSIHL Institute of Higher Learning. We'll assemble back here at 1:40 p.m. The venue for the lunch for the ladies, it is in the foyer in the main building, and for the gents, it is in front of the annex building, this building, lawns. Thank you. Sairam.